Hello, good morning. Can everyone see my screen?
Yeah, just pop by to say hi. All the best to your session coming up. Thank you.
Thanks.
Thanks.
Good morning. I think we can now get started. So I hope everyone can hear me. Okay, I suppose everyone can hear me. Welcome to the DGL tutorial. And before we actually really start the tutorial, I would like everyone to follow the instructions on my screen. So basically, for today's hands-on tutorial, we prepare a AWS SageMaker to set up the environment, the tutorial environment. So if you send an email to this email address, and then you will receive 2 emails. And then in the second email, you will get a Jupyter Notebook link. And if you click the link, then you get to an environment that you actually, it has everything. It will have the, it will have all the tutorials we prepared, and then you can, so if you click it, then you will see something like this. So it will have all the tutorial, today, all the hands-on tutorials. So you can just play with these notebooks. So if you have any questions or another option, one option is you can always send a message in the Zoom chat, the chat room, or you can join our Slack channel. So we also create a KDD 20 tutorial Slack channel. So if you go to our GitHub website, this github.com/DGLAI/KDD20-hands-on-tutorial. So if you go to that link, then you will find the Slack channel. You can click the Slack channel and join our, and you can ask a question there as well. So I will leave this screen for one more minute, so to make sure that everyone can follow the send an email to this email address, and then I will start to today's tutorial. Okay, so one person asked if the tutorial notebook is the same. Actually, the same. We just want to provide you an environment so you can you can run it during the tutorial session. And so we in this environment, it already has the GPU, so you can just you can just run the tutorials, and you can just play with the tutorials. We just want to save you the time to set up the environment, and that's all. So okay, I think we can get started. So today's agenda is today we are going to today's tutorial is the scalable graph neural network with the deep graph library. So we are a group of scientists from AWS, and here is today's agenda. So the first, we are going to talk about some overview of graph neural network, and we will then we will talk about what the overview of the deep graph library, the DGL, and then we are going to go through the hands-on tutorials. We will see how we can use how we can use develop GNN models for some basic tasks, and then we are going to see how we can train graph neural networks on a large graph. And in the last session, we are going to talk about how are we going to do distributed GNN training. So the first, for the first talk, I'm going to play a pre-recorded video.
To the tutorial on scalable graph neural networks with. Good morning, everybody. I would like to welcome you to the tutorial on scalable graph neural networks with the deep graph library. So the agenda for the day is as follows. So to begin with, we're going to have two presentations. They are PowerPoint presentations. So the first one will be give you guys an overview of graph neural networks, while the second one will be an overview of the deep graph library. After that, it will be a half-an-hour coffee break. And then it will be a hands-on tutorial that is going to cover a GNN model for basic graph tasks. After that, it will be a 1-hour lunch break. And then when we come back, we're going to have two hands-on tutorials. One will be on GNN training on large graphs, and the other one on distributed GNN training. So my name is George Karipis, and I'm a senior principal scientist at AWS Deep Learning Science. I'm based out of Palo Alto, California. I'm also a professor at the Department of Computer Science and Engineering at the University of Minnesota. And I'm currently on leave at AWS. You guys can get a hold of me if you want to contact me using either my Amazon email address or my U of M email address. So to motivate the use of graph neural networks, I would like us to consider three applications. Right? So the first application is that of fraud and abuse. And the goal over here is to be able to detect malicious accounts, identify fraudulent financial transactions, fake reviews, fraudulent insurance claims, etc. So the second application is that of recommendations. I guess most of us are aware what's the task over here. The goal is to recommend products, media, article experiences, jobs, and so on to individuals. And then the third application is that of marketing. And what we want to do over here is to be able to, to figure out to whom should I offer a discount, how to identify who are the influencers, so that I can market them directly. And another one may be identify which of my customers are most likely at risk of churning, so I can take some proactive actions to prevent them from doing so. Okay, now what is common in all of these applications is that they use graphs to represent the underlying data. For instance, in the context of FireMap use, if we're talking about financial transactions, usually there is a financial transaction network that is used to represent the relevant information. In the context of recommendations, usually what we have is what's called the collaborative knowledge graph that contains information about users, the different items they interacted, as well as any other information that describe the users, as well as describe the movies, right? So, and in the context of marketing, quite often, what I have access to is some form of a social network. Okay. Now, what's even more interesting is that I can use these graphs to solve the underlying problem by using machine learning approaches based on graph learning. Okay, so I can use those approaches to figure out, which are the entities in my network that corresponds to fraudsters. I can identify, for instance, which movie to recommend to a person, or can identify, which are the most influencing people in a particular social network, so that I can market them directly. So when we talk about graph learning or machine learning on graphs, we usually kind of consider three tasks. So the first task is that of node classification. The second task is that of a link prediction. The third task is that of a graph classification. So now within the node classification, the goal is to be able to predict the class or predict some form of value for each node in the network. And things like detect malicious accounts or target the right customers are instances of node classification tasks. In the context of a link prediction, the idea is to predict a missing link in the network. And that is actually the way I formulate the recommendation problem, because the recommendation problem becomes of predicting a new link, right, between a particular user and a particular item, right? So this is kind of the link that I'm trying to predict. Or another case of a link prediction is that predicting missing relations in the context of knowledge. And in the context of graph classification, the task over there is to be able to predict the class or predict a property of an entire graph. Okay. So a prototypical use case for graph classification is in the context of chemical informatics. So in which, what I'm like to be able to do is I would like to be able to predict certain properties for a particular compound. Right? For example, a very important property that a lot of people would like to be able to predict for a compound is whether or not that particular compound, will be able to treat a particular disease, right? So being able to predict that type of property then will help me in the task of drug discovery. One way to solve the various graph learning tasks is to use node embeddings. The idea behind those approaches is to embed the nodes of the graph into a low-dimensional space in such a way so that the embeddings capture the essential task-specific information. Now, once I have those embeddings, I can use those embeddings as inputs to traditional off-the-shelf classifiers, such as neural networks supported by machines or even decision trees, in order to solve the classification task at hand. Now, over the years, there has been a bunch of different methods that have been developed to compute those embeddings. Okay. One class of methods generate those embeddings by doing manual feature engineering. So if that requires domain expertise, involves considerable manual fine tuning, is in general time consuming and simply does not scale. And there's been another class of methods that have been developed and have become very popular, in which they generate those embeddings automatically using various unsupervised dimensionality reduction approaches. Things like singular value decomposition, tensor decomposition, cofactorization, deep walks, etc. are examples of some of those methods. However, the problem with those things is that they cannot effectively combine the attributes that quite often we have with the nodes and edges in the network. And that to a large extent, most of those models are mostly multilinear models. And they decouple the learning of the representation from the downstream classification task. So they do not allow for an end-to-end learning. So which begs the question, can we do better? Okay, and the answer to that question is graph neural networks, right? Graph neural network is a family of deep neural networks that learn node, edge, and graph embeddings. So the way graph neural network works is as follows. So we have a graph over here, and there's a particular node over here, let's call it target node, for which you would like to be able to compute these embeddings. So what the graph neural network does, it looks at an ego network around that node. And the ego network is a network that is centered on that node that contains all the nodes that they're up to k hops away from that target node. So once that ego network has been identified, okay, then it learns functions to compute the embeddings of the target node by taking into account information about the structure of its ego network, as well as the attributes of the different nodes and edges involved in that ego network. And that embedding that is computed for that node, right, is learned in an end-to-end fashion, based on the downstream, classification task. Okay, so graph neural networks were introduced, around 2014. I think some of the early papers around the time frame, and they have become extremely popular. I mean, this is a chart that obviously is dated by a couple of years, but the number just has is increasing at an exponential rate. So there's a lot of research on graph neural networks and a lot of excitement. And the primary reason for the excitement is that what graph neural networks allow they bring the power of deep neural networks on relational data, right? And quite often in most applications, relational data is significantly more predominant than non-relational data, things like images, text, video, and so forth. So really, it's just a way by which the advances in deep learning can permeate to many different domains. So another advantage that the graph neural networks have is that they can be trained together with a downstream task in an end-to-end fashion. And as a result, they can learn representations that they are very well suited for the classification task or link prediction task at hand. To give the idea about why the thing is happening is how the thing is happening is in the traditional method. What I have, given a graph, I use a traditional method of compute embeddings. When those embeddings are computed, then what I do is I use them as inputs to a classifier, in order to solve, let's say in this particular case, a classification task. Now, during this training of the classifier, right? So the gradients, propagate in this classifier's model parameters, and I will never get that supervision signal to actually go and change the embeddings, right? So I never have gradients, propagate all the way back into that model over here that computes, the embeddings of the nodes in the graph. On the other hand, in a GNN, what I have is I go from the graph, I apply my GNN models, I get the embeddings, I take those embeddings as inputs to another model that will give me the classification, and I use that model over here to predict the classes, right? And then when I backpropagate both on the model parameters for the classifier as well as the model parameters for the GNN. So what that thing allows me to do is allows me to actually train the GNN to compute embeddings in such a way so that those embeddings are well suited for this classifier in order to perform really well on this classification task, right? So, you can imagine that leads to much better performance than the traditional approach in which, those two things are not trained in an end-to-end fashion. And the final reason that why graph neural networks are better is because the fact that graph neural networks are inductive models because they learn the same neural network on all the nodes and edges in the graph. So remember from the picture that I have shown to you guys earlier, So what GNNs do is that they learn a function to compute node embeddings from the features of the node's ego networks. Okay? When those features do not encode information about the identity of the node itself, but correspond to features describing attributes and characteristics of those nodes, then those functions can be applied to any ego network to compute the representation of the target node. Okay, so remember what I said, So, and as a result, what I can do with that is that I can train a model, right, on some graphs, right? So I can use that model to learn how to compute a representation, let's say, of an individual, right? And I can do that thing in an end-to-end fashion. And once a GNN model has been trained, then when a new individual comes into my network, that individual was not there when I was training the model, but that individual does connect in the network. So there is an ego network that can derive from that individual. Then I can apply that model that I have already computed to actually compute an embedding, right? So you can think of a GNN as a computable embedding. So as opposed to the traditional methods that they learn an actual embedding, what GNNs learn, they learn functions that on how to compute those embeddings. Okay, so as you can see, that allows them to train to do really well for cold start settings, right? Allows them to train the model on a subset of the graph, and then apply the model on another part of the graph or an entirely different graph to actually compute embeddings and so on. Now, so one of the things that, as I mentioned earlier, the reason that thing works is because the model that they learn, right, they take advantage of the features that describe the attributes or characteristics of the nodes in the graph. Now, quite often, sometimes, we do not have such features, and what commonly is done is to do a one-hot encoding of the nodes in the graph, right? Once I do a one-hot encoding of the nodes in the graph, at that point in time, that inductive bias is lost, right? Because I have encoded in my function information about which were the nodes involved in learning that function. Right? So that differentiates what's called the inductive versus the transductive models, GNN models. Okay, so now that you guys have some high-level idea about what are GNNs and what are the problems that they're solving and how they work and what they're good for. Okay, I would like you guys to give you some example of some classical by now GNN models. So the very first model I would like to briefly describe is the graph convolution network, right? So this is kind of a graph equivalent of a convolution network for images. Okay, so in that network, the message passing function is nothing more as communicating a node's current embedding, scaled by the degree of node V, right? So the aggregation function is nothing more than the summation of those messages that were received, and the update function takes that aggregated message, multiplied by a weight matrix W, and then applies a nonlinear activation function to update the representation of the node, right? So pictorially, so given an input graph like that, then during each layer of the GNN, what happens for every node, it receives the representations for every node over here. It first aggregates the representations of each neighbors, so through over here. And again, that aggregation involves the neighboring nodes, right? As well as the representation of the node itself, right? So it adds those things up, and then it divides everything by the degree of the node V plus 1, right? So remember, the degree of the node V in this particular case, it will be 3 plus 1. So the end result of that part is nothing more than the average, right, of the embeddings of each neighbors plus itself. Okay, and then it takes that representation and then multiplies by dense matrix, weight matrix, right? And then does a point-wise, nonlinear activation, right? So in this particular case, the function I will use is, for instance, a value in this picture. So this is one hidden layer. Then this is one layer of the GNN. Then I can do the thing one more time. So again, this time now I'll be averaging the averages of the previous iteration, right? And I can do the thing multiple times. And each of those things will define a layer of the GNN, of the GCN. And then at the end, I'm going to get, for every node, the final representation of the nodes, going through that process. Okay, so again, this is a very simple network. So the only model parameter over here is that weight matrix. And this is a weight matrix in which on how the representation of the new representation of the node, right, will be computed as a function of the average of the representations of all of its incident nodes plus itself. So an improvement or a generalization of that model is, instead of just doing an unweighted average, to do some form of a weighted average and determine the weight by using an attention mechanism. So that gives rise to the graph attention network. So the idea here is, again, so I have the message corresponds to nothing more than the representation of a node at the previous level. Now, instead of divided by the degree, I have some activation weight, some attention weight, sorry. So then I take those messages and just aggregate them. And then I pass that aggregate message multiplied by weight matrix and then through a nonlinear activation function, right? And the way I compute the attention weights is using a standard, softmax approach, in which I have the embeddings of the source and destination of the two endpoints of the edge, right? And I first, project them using a matrix W, concatenate those things, and then learn a parameter alpha that will give me the dot product, and then using a softmax, I compute those attention weights. Another classical GNN is the relational graph convolution network. So this, in most real world settings, the graph on which I need to operate is actually a heterogeneous graph consisting of nodes of different types. And those different types nodes are connected of relations of different types. So what our GCN is designed to do is designed to generalize GCN, the graph convolution network, in such a way so that it will take into account those different relation types. And the way the thing is done is as follows. So what I have is and the best way to think of it is something like that, right? So so again, I have messages being sent, right? So the way that those messages are sent, instead of just copying the representation, just sending the representation of a node, right? Each node multiplies its representation by dense weight matrix, and the dense weight matrix is relation type specific, right? So that corresponds to the message. Now those messages are aggregated, right? And then that aggregated message is used to update the representation of the target node by first multiplied by weight matrix and then applying a nonlinear activation function, right? So the key difference between the way the different relation types are handled in the relational graph convolution network is by having those relation type specific weight matrix, right? That is used to generate the message to be sent to the target node. Okay. So I'd like us now to switch gears and spend a few slides to talk about how to train GNNs in end-to-end fashion. So remember that an layer GNN, what it does is it computes a representation for each node in the graph, right? And then each of those, and then this representation is fed into a downstream model, which is often an MLP, to compute a prediction. A loss function is defined, and gradients are backpropagated all the way, to the MLP model parameters as well the GNN model parameters, right? So this is the picture that we saw earlier over there, right? So I apply the L layer GNN that is over here to compute the representations. That classifier over here then represents to a classifier, to a model, and that is using MLP. And something gets computed over here, the prediction is computed, the loss function is defined, and then then the gradients are computed and backpropagated all the way out to both the model parameter for the classifier as well as the model parameter for the GNN. To make the thing more concrete, let's look at the problem of node classification. So in this case, what I have a bunch of nodes in the graphs. Now, for some of those nodes, I know they're labeled. Now, for some of the other nodes, I will not know for their label. For the ones that I know they're labeled, I will compute their representations, and then I take those representations usually through an MLP, and then define a loss and backpropagate, right? So a typical loss defined is a cross-entropy loss, and this is how something like that will work. So recall from the previous notation that H sub V superscript L is the representation of node V after L layers of a GNN. Then W over here are the parameters of the MLP, and label is the actual ground truth label for that particular node. And then I define a cross-entropy loss, and using that I will do backpropagation. So remember I mentioned over here in a semi-supervised setting, so quite often when I want to do node classification, only a subset of the nodes in the graphs will have labels. It's only for those labels for which I define the cross-entropy loss, and I ignore the rest of the nodes. Now, the rest of the nodes and their features are used while I compute the embeddings of the nodes with labels, but they're ignored when I define the cross-entropy. Okay, so in order to supervise link prediction, we first create a loss function that rewards the pairs of vertices that are connected via edges. Now, those edges are usually called the positive edges. And at the same time, it penalizes the pair of vertices that they are not. Usually those called the negative edges. Okay, so we have the loss function that rewards the positive edges and penalizes the negative edges. In order to be able to compute that reward, right, to measure that reward, what we usually do is we define a function whose score should be high if a pair of vertices are connected via an edge, otherwise it would be low. Okay, and a common function that people use to compute that score is the sigmoid of the dot product between the GNN derived representations of the two nodes involved. Okay, so now let's make that thing a little bit more concrete, right? So so my goal is to score the presence of the edge between 1 and 9, right? So what I do is I use a GNN to compute a representation of node 1. I get the GNN to compute a representation of node 9, right? And then I have a score function, which is that is the dot product of those two representations, that the HV will correspond to 1 and the HW will correspond to 9, for example, right? And attach that into a sigmoid function. So this is a function that measures, right, that should be high, right, if there's a real edge between 1 and 9, and should be low if there's no edge between 1 and 9. Okay, so we have now defined all the different pieces. Now the loss function, what we do is usually, for every positive edge that we have, right? So we generate a set of negative edges, and the way that we generate those negative edges is by randomly sampling a pairs of vertices, right, that they're not connected via edges. right? And then for both the nodes involved in the positive edges and the nodes involved in the negative edges, right? So we compute their GNN-based embeddings, right? They compute the associated dot products and the sigmoid of the dot product using that, and then we optimize the loss function, that's defined over here, right? Which it encourages that the edges, the positive edges to have a high score, and the negative edges to have a low score. Okay, and again, so this is the end-to-end loss function. So you can think over here when I do propagate gradients, those propagating gradients go through those embeddings, of HV and HW, right? And similar over here, and those embeddings will, will be computed the output of the GNNs, so that will also propagate, backpropagate the gradients to the GNN model parameters. Finally, for the graph classification problem, so this is somewhat different than either the node classification or the link prediction, right? Because what GNN does is used to compute embeddings for the nodes. In the case of the class classification, what I would like to do is I would like to be able to predict something from the entire graph. So in that case, what I do first is I do a readout of all the embeddings of the graph, right, into a single representation. So I have some sort of a readout function, right, and that can be potentially a trainable function. Okay, and then once I have a single vector representing the graph, right, then I can usually use a cross entropy loss. I have its own weight metrics, or that can be potentially an MLP, right, to define the loss, and then backpropagate from that loss to G, and then from G through the individual representations of the nodes, and then from those representations of the nodes to the GNN model parameters. Okay, so finally, the last part I would like to cover is how to train very large GNNs. Okay, and there are many applications out there for which we need to train GNNs on a very large graphs. Some of those graphs can easily contain millions of nodes and billions of edges, right? And quite often those large graphs arise in settings in which the model is sometimes transactive in nature, even though I may still have inductive large graph training problems. Okay, some of the domains in which those things arise, like social networks, you would like to be able to compute embeddings for individuals in very large networks, and the recommendation set in computing embeddings of millions of products and millions of users, as well as in a very large knowledge graph. Okay, so one of the challenges in training very large neural networks is if I want to be able to take into account, take advantage of accelerators such as GPUs, then for very large graph, it's simply not feasible for me to load all the data into the GPU memory, right? So in order to be able to do that, then I have to actually break the graph into smaller chunks, and a typical way of doing that is by employing some mini batch training. So the idea of a mini batch training is as follows. So remember that that in a GNN, what we do is we compute representations of nodes, right? And those things are supervised in an end-to-end fashion, right? And to a large extent, the individual training datum in a GNN is that of a node that usually refer to that thing of a target node, right? So I can create a mini batch of size 1, right? That has a single target node, right? By just extracting its ego network. Okay, so this is a mini batch of size 1. And if I want to have a mini batch that is larger than size 1, then I will usually select a subset, like a small number of target nodes, right? And I compute the ego networks, and the union of that will define my mini batch. So I mean, this is a reasonable way to control the complexity of the problem, to reduce the complexity of the problem. However, the caveat with that approach is most real world graphs, they tend to have a power law degree distribution, right, or correspond to the small world graphs. As a result, what can happen is even if I focus on a single target node, right, and I expand an ego network that is 2, 3, 4 hops deep, right, that can easily, include an extremely large number of nodes, right, especially if I hit some of the high degree nodes in my graph, okay? So that my initial goal of creating a mini batch such that its memory footprint will be reduced, so that I can be able to leverage, GPUs for high computational performance, cannot really be achieved. So in order to deal with that, most mini batch based training algorithm for GNNs, in addition to creating a mini batch by focusing on a small number of target nodes, they also employ various neighbor sampling approaches to reduce the size of the ego networks, right? So the simplest neighbor sampling approach is a degree-based, is a neighbor sampling based on a maximum degree. So for instance, I can put a bound. I will say that for every node, I'm going to only sample up to 2, no more than 2 of its neighbors, right? So then in that case, I can guarantee that the maximum size of the ego network associated with the particular target node is bounded by the maximum degree raised to the depth of the network, right? So this is the case in which I have a neighbor sampling which I put a bound of 2 on the degree of the maximum degree of the nodes that I will, the maximum number of neighbors that I will be sampling. Okay, so. But again, this is just one of the sampling strategies. There are a number of different sampling strategies have been developed, right? And but the primary design goal for those sampling strategies is to be able to deal with the fact that without sampling, I can potentially run into some serious, computational problems and memory problems. So finally, to summarize, so there are a lot of problems, right, that can be solved by formulating as graph learning problems. And for this class of problem, the graph neural networks represent probably the current state of the art technique for solving them. They have a number of advantages over traditional approaches. And because of these advantages, right, it's has become both a very exciting area of research, and also GNNs are increasingly find their way into a wide range of production applications. And I personally expect the number to continue to grow. Well, thank you very much.
Okay, so does anyone have any questions related to this session? So I see someone asked questions in the chat room. So maybe you can address those questions first. So I mean, for some of the sessions in today's tutorial, we are just going to play some pre-recorded video. So I think I can try to we will try to address the questions in the chat room first. And in the end of the video, then you can ask your questions and we will answer the questions. Okay, so one question is, what is the difference between node classification and a graph classification? So basically, for the node classification task, what we want usually is we want to make a prediction on individual node. So let's say we have a graph with like 1 million nodes, right? So we want to make a prediction for each individual node. And in the case of graph classification, we want to make a prediction for the whole graph. So one example is if the social network, the node classification task is to say we want to predict if you what is the job of individual person in this social network. And for a graph classification, the task is probably we probably want to predict what is the property of the entire graph, entire social network. So, for example, what kind of I don't know how to make so I guess a graph classification is kind of common in some applications, for in the chemistry. So for example, we can represent molecular as a graph, and then we want to predict what type of molecular it is for each graph, something like that. So another question is how to choose, are there any reference that discuss how to choose optimal number of neighbors? So I suppose this question, another question is about how to choose the optimal number of neighbors, or is this based on domain knowledge or business aligned alone? I suppose this is talking about the neighbor sampling technique George was discussing in the video.
Yes.
Okay, so usually our experience is, of course, this definitely varies from data to data. So our experience is as long as we choose sufficient number of neighbors, then the model usually is trained pretty well. So by sufficient number of neighbors, usually what we choose is like 10 or 20, something like that. It's we do not need to sample too many neighbors, like 100. We never really try that, but usually when we try the 10 or 20, usually it works fine. So of course, this number must varies from data set to data set, right? We haven't tried all data sets, so we cannot tell you for sure. But usually it works fine in our experience.
So essentially, the number of neighbors is just a hyperparameter, as if you're tuning other hyperparameters such as learning rate or others.
Okay, so it's not really a statistic that you actually can ascertain or develop from, I guess your whatever sampling procedure you're performing, I guess.
Although that will probably be an interesting direction to determine the optimal number of neighbors for each data set, or like the number of or the optimal probability of choosing a neighbor. For the latter, I once saw a paper that does this using Bayesian or some kind of variational approach, but I think overall there's like only a few of them doing this.
Okay, thanks.
Okay, so the next question is, does relational graph convolution network deal with multiple types of edges between the same pair of nodes? I think the answer is yes. So the projection matrix is related to relation. So you can there can be multiple relations between one pair of nodes, and then we can just apply those projection matrices. Is there any commercial? So next question is there any commercial graph database systems with native implementation of GNN techniques? I guess we haven't seen any graph database integrated with GNN yet. So I will believe some of them will be integrated very, very soon. So in the final slides, suggestion was made. So another question is, in the final slide, the suggestion was made to randomly select neighbors for mini batch. Are the labels selected multiple times with a random number of neighbors or only once? So I guess so first, when we perform mini batch training, we will make a prediction on each node. Actually, because we run this, usually a model is trained with epochs, right? So that means we make during the training, each of node is trained multiple times. So each time we will sample a different set of neighbors and then make a prediction on this node. So we will randomly sample neighbors for a single for each node multiple times. I think that is what your question is.
Yeah, that was exactly my question. Thank you.
So are there examples? So another question is, are there examples of GNNs being used for community detection? Or is the typical approach to generate node embedding and clustering those node embeddings with a standard clustering technique? So when you say community detection, I would guess you mean so those typical clustering algorithms for graph. So basically, this is you want an unsupervised method to cluster nodes in a graph. Do I understand right?
Yes. So either clustering, but I'm also interested in like seed set expansion sort of approaches. But clustering is probably a good one.
Okay. So if this is an unsupervised task, I think usually. Okay, so Chen, do you have any comments on this? So my experience from what I have seen so far, usually if we want to do something like that, we want to train node embeddings in an unsupervised way. And then later on, we can run, like, for example, k-means or other clustering algorithms on this on those node embeddings, pre-trained node embeddings, to generate the clusters. That is something I can think of. Chen, maybe can you do you have more comments on this?
Yeah, I think in the literature of graph neural networks, usually what we do is just learn the node embeddings in unsupervised ways, as Don mentioned, and then apply some standard clustering techniques. There's also some kind of spectral clustering, which is also unsupervised, but yeah. So probably, yeah.
Yeah, so I think, I mean, so for this kind of problem, I mean, because the entire task, the entire setting is unsupervised. So I guess, I mean, that there isn't the only way is to train the node embeddings in an unsupervised way first, and then do any clustering. So but when you say community detection, so in some settings, they can also have some labels, right? So in that case, then we see more techniques of doing community detection. But I guess it's really depend on the setting. Does this address your question?
I think so. Do you have any further details? You said in the settings where you do have labels, you're able to use GNNs. Is there an example of that?
I mean, like if you have labels, you can then formulate this problem as some kind of semi-supervised node classification problem, right? So so when you do kind of semi-supervised, so when you have the labels, then of course then you can train your node embeddings better. Right? So instead of completely unsupervised, you can do some kind of you use the existing labels to train the node embeddings first, and then you whether or not depending on how many labels you have, then if the label either later on you can do you can make a prediction on each node directly with the trained graph neural network. So this will be very similar, or this will be exactly the same as what George showed as a node classification, right? Or you can just think this label as some supervision to further tune the node embeddings for the downstream task, and then you get a better node embedding. And then when you have the better node embedding, you can potentially, when you apply the clustering algorithm, you can get a better clustering result.
Got it. Okay, understood. Thank you.
So another question is why is it important to embed nodes to a low dimensional space? So I guess let's go to the slides that talk about why. The typical way to perform a graph machine learning task is to first to embed the nodes of a graph into in some embedding space. So the reason is I mean so the question is why do we want to, why do we need to have embedding? So I mean, so most of the machine learning models need to make a predictions on some embedding space, right? So suppose, I mean, we can think of a graph itself as its each node is if a node is represented by its neighborhood, by its neighbor, then this a node is the representation of this node is very, very high. So it has many dimensions, basically. So if we apply any machine learning models on this kind of representation directly, usually it will have a lot of means this model will have many, many parameters. And usually this model, we cannot learn a model very well. So a typical approach is we want to learn a lower representation first, so that in the downstream in the model for the downstream task, the model will have much smaller parameters, so we can learn a model much better.
Thank you.
So any thoughts on integrating node content into GNN can be associated with? So another question is about how to integrate the node content into GNN. So actually, one advantage of GNN is it can easily integrate or naturally to integrate graph structure and with the information on node. So this is by default, GNN is capable of doing something like that. Remember, so when we apply, we perform GNN on a graph, we will get some node input features into the graph neural network, right? So is this the question you're asking, or what you are really asking is, what happens if the node has some raw features such as text or image? How are we going to deal with that? So is this the question about how to deal with the raw features?
Yes, exactly.
Oh, okay. So one way, I think a typical way is what we are doing is we for text, if we have a text, right? We probably want to run, for example, BERT on this text, on this sentence or in a paragraph to generate an embedding. And then we use those embedding as node feature to run graph neural network. If you have an image, we can do something very similar. For example, we can run ResNet to generate, suppose you have a pre-trained image model. And for example, you have a pre-trained ResNet, then you run ResNet on it, and we get some, we get the embedding that output by from the ResNet, or maybe the last few layers, or we'll get the output of the last few layers of ResNet as the embedding generated by the model. And then we feed this embedding into a graph neural network to compute, to generate the final embedding. Of course, we can the other thing is we can do is we can really train it in an end-to-end fashion from the raw feature. I haven't really seen people. So Chen, have you seen people are doing things like that, really from end to end?
No, I don't think so, especially for industrial applications. Yeah. So for instance, PinSage extracts the image and text textual features using pre-trained, I think whatever convolutional and for a text, I think it's fast text. I cannot remember actually, but they use pre-trained models. They don't train it end-to-end fashion.
Yeah. So usually, if we really want to do this end-to-end fashion, it is, I guess, it is a very computationally intensive. So people usually don't do that. Okay. So the next question. So the next question is there for node class for graph classification, is there a recommended way on how to combine those node embeddings into a single graph embedding? So the typical way is to do average or max pooling. So question is, if we do something like that, will that cause information loss? Then the answer is yes, definitely. If we just you do the average pooling or max pooling over all the nodes of a graph to generate the graph embedding, the graph embedding will definitely lose some information. So I should say whatever most of the ways I think when we generate the graph embedding, I think almost all the ways all the method will lose the information because we are reducing we are generating a fixed dimension size, right? So it definitely loses information. The question is, what is the best? How can we learn this learn a way so that we can lose less information? One solution is actually there was a paper about how to generate the graph embedding in a hierarchical way. So basically, instead of average over all the nodes at once, where we can do some kind of like clustering first. So we can and then we basically we will do this hierarchical clustering. And then in each level, we average, we do some kind of aggregation over the nodes in the cluster. And then finally, we get a final embedding for the graph. I can refer you to the paper maybe afterwards. I don't have the paper at my hand right now. So maybe Chan, you know which paper I'm talking about, right? So could you send the link in the chat room?
I'm sorry, I don't quite get the paper content.
So basically, it's from Yuri's group. So basically, it does the hierarchical clustering, but they learn this hierarchical clustering in an end-to-end fashion as well.
Oh, is it diff pool?
Oh, yeah, sorry, diff pool, yes.
Okay. There you go.
So what is the effect of missing data or missing edge in GNN best practice? So I think graph neural network should be able to deal with the missing edge. Should be able to deal with it. I mean, like think of when we all the graph, it should be pretty noisy, right? It should have a lot of missing edges, or there should be a lot of unrelevant edges. So for those graph neural network models, we a lot of time we do average, right? So or do some kind of max pooling or something like that. So those models usually will deal with missing edges fine. In regard to have you experimented with each other activation function? So another question is, what is the best activation function we can use on graph neural network? So Chen, do you notice any people use different activation function in their model?
No, I don't think so.
Yeah,
probably that's the context of I don't know, neural architectural search or something like AutoML. Like if we use some AutoML techniques, then like switching the activation functions can be an option. But for as far as I'm aware of, I don't think any paper in particular in particular compares the effect of different activation functions.
Mm. Okay. So
Thanks
for the next question. So next question is, what is the main components of a large-scale production GNN recommender system? I think that the main component is basically how are we going to generate a mini batch and train this whole graph neural network in a mini batch fashion. So I mean, I guess the first commercial GNN recommender system model is the pinch model, and what it does is they do some kind of random walk in the graph to sample neighbors for each particular for each item, and then and in this way it generate a mini batch and then train this the graph neural network to compute the item embeddings. So I think the most important thing is, and they claim they can scale to a graph with billions of items. So the most important technique in that model is basically how to sample this mini batch.
But in terms of the overall GNN Rexes system in production, usually the GNN is only responsible for generating the embeddings or like the representations of the nodes as dense vectors. So GNN itself is only like a small component of this huge Rexis pipeline. And during like deployment or like during production, usually people just search for the relevant items using standard nearest neighbor search techniques or other relevant stuff. So for instance, PinSage, after PinSage learns the node embeddings for each pin for the Pinterest, for the Pinterest data set, they recommend similar pins using nearest neighbor search.
Right. Yeah, thanks. So for the next question, why do we choose average over all? So another question is, why do we choose to average over all the nodes? Are there not any other measures that we can use? So I suppose this is referred to how to compute the graph embedding. So I think to compute the graph embedding, I think I don't think average is the only option. So for example, that this pool, they does this hierarchical way to compute the graph embedding, and so there is a learnable way to perform this reduction. For example, if there is previously there is a model called the set transformer. So basically, it is to compute the embeddings on a set of items, and then when we want to compute the embedding over a set of nodes, we can also apply a set transformer on the data. So I don't think average is the only option here. So there's so basically we can use some kind of attention mechanism to average over a set of nodes. Okay, so maybe this I'll answer the last question. Then we will go to the next session of this tutorial. So a question is there any rule of thumb for how much label data we need for GNN to be effective when trained in a supervised way? I guess it's not we cannot give you exact number or something like that. So typically when we use the graph neural network for node classification, for example, we always actually this entire problem is kind of like a semi-supervised. So that means when we train the model, we do not just use the data with the labels. We actually use the data, the label nodes as well as its neighbors, right? So typically when a data has a fewer label, so a data set has a fewer label nodes, then GNN can take more advantage of the data. And so suppose the suppose the data set has really a very few labels, then we will also use the graph structure to as some kind of signal to train the node embedding. So it's kind of like so let's say a data set doesn't have any labels, then we will just use an unsupervised way to train node embeddings. So when we do something like that, actually it's also pretty effective. And we have seen a lot of works that pre-train node embeddings. So I think a graph neural network is always very effective for whatever the number of labels we have.
Yeah, and also you can always treat the edges of the graphs as labels if you combine let's say, supervised node classification with this link prediction task, which is what GraphSage paper does.
There was a talk yesterday from the name escapes me. I'm sorry, but I'll post it in the chat in a second. But he did talk about there's other methods that they're exploring using semi-supervised approaches that might be of interest to the initial question, or whoever posed the initial question.
Okay, so something like
Cool. Thanks.
Yeah, cool. Okay, so now let's switch to the next talk of this tutorial. Let me share the screen. Actually, now the video I'm going to play is from the website. Let me send the link of this website first. So in case there is the video quality is not good, then I think you guys can go to the website, maybe watch it directly. So I'll send the link again. I hope everyone can see my screen. Let me see if there's a better way. I guess the best way is to do the full screen. So yesterday, the tutorial organizer recommend to use a lower resolution. So I don't know if when I play this video, the resolution will be better than the previous one. Let's see.
All right, let me get it started. Hello, everyone. I'm Zizi. I'm a faculty from NYU Shanghai. I take leave of absence to join AWS. I'm now leading the AWS Shanghai AI Lab. Thanks for having me. On behalf of the team, I will give a brief overview and update of DGL. So one of the most exciting research area in my view is deep learning on graphs or graph neural nets. As you can see from this deltas of keyword changes, the trend, you can see that graph neural nets is leading the pack. And there is a good reason that it is interesting. Now, graphs are everywhere, right? It represents a new class of data that's non-nuclear, right? You have, for instance, a molecular graph. In this graph, the nodes are the atoms and the edges are the bonds. And if you can compute the representation of such a molecular graph, you can predict its attributes, its properties. Another example is knowledge graph, where you have entities who are persons, books, universities, and whatnot. And the edges are the predicates, right? And this represents the knowledge in the graph format. Another common graph is for user and product bipartite graph, commonly seen for e-commerce for recommendations. You know, a user can buy different products over different time periods, and the product could be purchased by different users over time. So this bipartite graph encodes a lot of rich information. It can help you to recommend the relevant products to a user. Now, let me just give you example, a concrete example of a book that we just finished. It's called Drug Repurposing Knowledge Graph. Here, what we have done is to combine the data sets of 6 different sources with respect to drugs, genes, and diseases, and so on and so forth. It is perhaps the largest and most comprehensive knowledge graph out there. The graph has more than 100,000 entities with 13 different types. So those could be compound, which is a drug, right? And the genes. So a compound can activate certain genes or deactivate that. So this compound can treat certain diseases, but could have certain, side effects. Now this problem is basically a link prediction problem. What we want to do is to find similar compounds that target similar diseases. And what we find is 11 out of top 41 are already under clinical trials. So that is quite promising. So we have made this available to the entire community, so entirely open source, including the data, pre-trained models, and other tools. That is just an example. Let me step back, talk about what our target users are. When the project started in early 2018, we saw there is no good platform for deep graph research. And that is our first target users, right? You can find this under dgl.ai. It contains the core and some models and modules and so on and so forth. And that is for the deep graph researchers. The second users, as we find out, are deep graph domain scientists. Now, these domain scientists not necessarily want to reinvent or invent on the model, but they rather want to apply the model to their problems. And for those users, we develop DGL domain packages. There is for knowledge graph embeddings, there for bioinformatics, and we will develop and release more. Now, the reason I'm saying there's 2 packages is because although they share the same requirements, for instance, good documentation, good performance, complete models, and so on and so forth, they have different requirements in terms of user experience. In particular, flexibility is what the deep graph researchers wanted, so that they can innovate on new graphs, on new models, and domain scientists probably want turnkey solutions. Now, both those packages are open source. Since the development of this project basically moves to AWS, we can combine, and we actually do combine this with AWS proprietary services so that we can offer value to our end customers. So there is a third customer, which is the paying customers. And already we have DGL-based solutions deployed in various companies. Now let me first talk about DGL for GNN researchers. The basic formulation of deep graph is quite well known by now, but I thought it's always interesting to start with a problem, or rather a question that is related to our daily experience. Let's just say that hypothetically we want to compute an embedding for every person on this earth. And what does that take? Well, obviously your DNA defines you, right? That you can think of this as like no features. But just as important is how you interact with other person or other nodes, other DNAs, right? Those interactions can be dynamic, can change over time. They can converge to some stable set. But regardless, the interaction with your neighbors and the iteration of that also defines you. So in a way, you can think of graph neural nets. It's very intuitive. You can think of it as a structured data augmentation. Now, bear in mind, the graph's not necessarily complete. It can also be noisy. That's why link prediction is such an important research problem in the space of graph neural nets. Mathematically, there is just 2 functions we need to manage. The first one is the message function, which takes a connected pair, right? Looks at a connected pair, takes their representations, and also the edge feature if it's present. Not necessarily features, I'm sorry. It's representation. We computed a per edge message, and now you reduce them to per node. Then you combine with your own representation and you update. And you can go on this for many layers. So in DGL, we have the core abstraction called DGL graph, which stores your data. And you can access features of the graph, feature of these nodes or edges in a very easy dictionary style kind of interface. And DGL graph offers some other useful APIs for you to manipulate and query the graphs and perform computation. Now, speaking of computation, you already said earlier that you need to define what we need to define. Basically, the edge-wise, the edge-wise computation and also node-wise computation. And when you do need to update all the node representation in the graph, you just call g.update all. Or you can call that on a subset of the graph. Likewise, you can apply per node transformation using apply edges. Now here's a real world example, not necessarily the highest performing one, but give you the idea that you have the graph and when you update, you call update all. It takes in 2 arguments, message function and reduce function. And here is how you implement message function and reduce functions. There are certain built-in functions that we made it easy for you to specify and very fast performing, or you can implement in any arbitrary Python interface, right? This is computes the edges, message on the edges, or this reduce transforms, updates. Now map it down to the computation kernel. We find out that it's interesting that the computation essentially boils down to 2 general kernels, one on edges, another on nodes, and they can be generalized. It's a generalized sparse matrix multiplication for edge-wise computation, for instance. For node-wise, I believe. It's a second kernel that you can use that to compute attentions. Now, although you can simplify to 2 computation kernels, doesn't mean there is just one implementation and that will work very well. Just to give you an idea, right? To get high performance, what you need is parallelizations, and it depends on different strategy. You can do node-wise parallelization or edge-wise parallelization. Both are legitimate choices. Now, what turns out to be true is that each can depend on different factors, right? The storage format of your graph turned out to be a factor. So it seems to me that it is fertile ground to apply machine learning itself to optimize system performance. To give you an idea of the DGL performance, we compare DGL with PyG, which is a very good package. It's only available on PyTorch. Now, we look at GPU performance and CPU performance. As you can see, for some simple models, the performance of the 2 frameworks or 2 packages do not differ that much. But if you have a more complex model where you need edge features or attentions, the DGL is far better, especially for memory efficiency, right? Which is a precious resource for GPU. Now on CPU, you have a lot of memory. You can compute a large graph, and for that, the DGL offers a much better performance than PyG. Although you can see if you can compute on GPU, it can be quite a bit better. Now let me talk a little bit of what we do for the application builders. One thing that DGL does, which no other packages do today, is to be framework neutral. What does that mean? Why do we bother to do that? Well, the thing that the application of a GN does not take just a model. You may have a feature extractors. You may have data loaders. You have feature extraction and preprocessing and so on, right? To build a complete application is different from building and develop research as a model. What we want to make sure is that the model specific stays unchanged, and is independent from different frameworks. And we do this by using the old system strategy, which is take control of only the minimum and the critical. Basically, whatever that's in the DGO graph, we control. And we leverage the rest from the frameworks. Could be outgrad, memory management, dense operators. At the beginning, we also leave the sparse tensor operators to be handled by different frameworks, and it turned out to be a mistake because sparse tensor operators at that time wasn't very well performing. And we moved that into DGL graph. So I think we learned a lot of good lessons, and this is applicable for anybody who wants to develop a domain packages, especially when you want it to be real-world ready, given that there are so many a diversity set of frameworks out there. Now here is a side-by-side comparison of the same model implemented in PyTorch DGL and TensorFlow DGL. As you can see, the model specification part is exactly the same, right? What is different is like some framework specific things. What are those things? We'll look across different set of different models. You can see they fall into 3 categories. It could be model class inheritance, submodule and the parameter initializations, or framework specific operators. It looks substantial, but remember, for a developer who is familiar with the target framework, it's quite straightforward, and the model itself stays unchanged. What is very important though, and I find it quite interesting, that achieving framework neutrality doesn't mean that we will have to sacrifice performance. For instance, if you look at PyG and DGO, the PyTorch version, we see that DGO PyTorch performs worse for small graphs, but it catches up and actually performs better for larger graphs. And compare with GraphNets, which is TensorFlow native, DGL actually performs quite good to begin with, and the margin increases as it goes to larger graph. So let me talk a little bit about domain packages. So domain scientists are people who solve real-world problems. Well, they know their data very well. They know their data inside out. They know their problem space. They want to apply deep graph as a novel solutions to their problems. They don't necessarily want to tingle with the models. They want turnkey solutions and perhaps AutoML to help them to select models or hyperparameters. And we make sure that it is easy for them to use. For now, we have released 2 packages. The first package is DGOKE, which does knowledge graph embedding. It achieves model-wise sort of performance, but also system-wise. If you train it on 4 machines, it can complete the training of 4 freebase in 30 minutes. And we can use DGOKE to derive other applications and applications in domain application. For instance, the drug discovery repurposing knowledge graph is an application of DGOKE. The second package, which we actually developed earlier than DGOKE, is for bioinformatics. And here we have molecular property predictions, generative models, ranking prediction, and so on and so forth. Again, we guarantee sort of performance, and comparing with the tools that those scientists use, it's quite a bit better. Now, if you look at the overview of the stacks of DGL, you have GPUs, CPUs, clusters, that's the hardware side. And you have frameworks like PyTorch, Mixnet, and TensorFlow. And on top of that, and coexist with those, we have the DGL core. On top of that, we build domain packages. Our principles are to make sure that we help people to develop new models as easy as possible. And to be real world ready, we want to be backend framework neutral. Of course, we want to guarantee the performance. As I said, real world readiness is important. So DGL released the first version in Europe 2018. So about a year later, it is released as a managed service on AWS reInvent. And in April this year, we released support for TensorFlow and the 2 domain packages. Adding with them to the release is sampling for dealing with large graphs. We're going very quickly to 0.5 release. We were hoping to have it out yesterday, but we're going to have a delay of 1 week or 2. In 0.5 release, we'll have the kernel optimization in the main trunk. We understand that the documentation of DGL is not the best. It has large room to improve, so we are working very hard on that. And very importantly, we're going to release a large-scale distributed training for giant graphs. So DGL distributed is fully distributed, meaning its components, some of which are already in DGL-KE, and some of them are new in this release, are all distributed. They can run on different multiple boxes. You have storage part, you have the training part, you have the private server, you have graph sampling part, right? And the graph is partitioned across different devices in the locality sensitive and locality aware fashions to maximize performance. Of course, we want to have linear performance, linear speed up. What is important is for user to not to see too many changes. Now here's an example. The code here works just for single process. And this is a code that you need to modify so that you can have the same code run on distributed training. There's partition and there's loader, and that's all that you need to change. Before I wrap up, I want to talk a little bit about other applications. We have been talking about so far that is completely where the graph is ready, right? It's on the non-Euclidean data for graphs. But I think it's also very important to work on unstructured data and discover the graphs. Let me give you an example as a problem of images. It's not so much about there's a person and there's dog in these images, it's rather their relationship. Those objects and their relationship in the computer vision community called scene graph is what really matters. So embedding this graph inside of the object itself is a much more meaningful way to say that we finally understand an image or a video. So DGL's implementation of this particular model is 3 or 4 times better. Now this is where the graph is ready. A more challenging problem is the graph is not there. We have to discover that. And the work that we have just completed takes a body of text, extracts the graph out of it, and then takes this graph and map it back, right, in a cycle training. We are able to show this back translation or cycle training actually achieves better performance than a supervised fashion when the parallel data is available, meaning we don't assume the graph and text are necessarily paired. As long as they are following the same distribution, meaning they're describing the same semantic thing, we will be able to apply this technique. As is everywhere, the hardest problem here is labeling the structure is extremely labor intensive, expensive, and error prone. To that end, we worked hard and we are going to release a data set that is much bigger, about 100 times bigger than the dominant graph text dataset, WebLNG. So it's a dataset which contains 1.3 million weakly aligned graph and text pairs. And I'm excited for other people to use that. Now, that's the end of my presentation. I appreciate your trying out DGL. I want to make sure that your feedbacks are received, and please give us your suggestions, opinions, and whatnot. And we'll also welcome your contribution. Thank you very much.
Is there any questions for this session? Okay, so if there are no questions for this session, I think we can have this virtual coffee break first. But before that, so I don't know how many of you has already applied, send an email to the email address I mentioned at the beginning of the tutorial. So if you did, then by now you should already receive 2 emails, and you should already get the notebook link. So one thing I want to mention before the break is when I run this notebook from the SageMaker environment, I realized actually you might need to choose the label correctly in order to really run the notebook. So let me see if I can show you how to set the kernel correctly. Actually, sorry, I just realized I do not have the link I have actually is already expired, so I cannot really show you now. I will try. I'm going to apply a new one, and then show you how to set up the kernel correctly in order to run the tutorial in the notebook environment. Let's start the hands-on session in about 20 minutes. So it is originally the scheduled time is 11 a.m. Pacific time. So so it is about in 20 minutes. So we will let's have the break and then restart the tutorial. Thanks. So actually, I mean, if anyone want to have more questions, we can continue discussing. Okay, I will just share my screen so anyone can see what the email address is. So if you send the email now, you probably will receive it in hopefully in 10 minutes. And the session, the next session will also start in 10 minutes. Let's restart. So for anyone who just joined the tutorial, so now we are going to have the hands-on session. So anyone who want to play our notebook, our tutorial during the hands-on session, then you can send an email to this email address, and then you will get 2 emails. And the second email will give you a notebook link. So you can click the link and then you can start to play our tutorial in this SageMaker environment. So basically this is a Jupyter notebook environment. And when you run the DGL code in this environment, you need to choose a kernel, a conduct kernel, so that so this is users need to choose this conda DGL workshop kernel. So this environment, this has already we have configured all the environments required for running the notebook. So if you have any more questions, we can discuss it in the chat of the Zoom. Now let's go to the third session. This is a hands-on session about how are we going to implement a graph neural network model in DGL for basic graph tasks.
Hello everyone, welcome to this hands-on part tutorial in KDD 2020. My name is Mingjie Wang. I'm from Amazon AI Shanghai Lab. I'm also one of the core developers of the toolkit called Deep Graph Library, DGL. So this is a hands-on part about how to scale graph neural network training with DeepGL. So you can expect you will see some code, play with DGL, and maybe answer some questions. Unfortunately, we cannot meet in person, so we put all the tutorial contacts available online, so you can see them at the GitHub link below. And for any questions, please join our Slack channel. You can scan the QR code here. We welcome any issues or feedbacks when playing with DGL, or just some general discussions about graph neural networks. Today's topic is about scalable graph neural networks with DGL. So let's first look at several scales of graphs in real world. So we roughly divide the different graphs according to their scales into 3 categories. For the first one, these graphs are usually small. They have less than 1 million nodes. A typical example is protein-protein interaction network, where each node is a protein and the edge is the interaction between different proteins. And since these graphs are small, we can put all the graph data, their features and structures to the single GPU for acceleration. On the second level, we have median graphs, where the number of nodes can grow up to 1 billion. So this scale is actually the most common scale you will see in the open academic data set, such as citation graphs or most of the graph data sets in Open Graph Benchmark. Since these graphs are relatively larger than these small scales, we usually cannot fit all the graph data in a single GPU memory. So we need to, instead of training on the full graph, we should train it on a subgraph. And also we can issue them to different GPUs to further speed it up. To the very end, there are giant graphs. They can have tens or even hundreds of billions of nodes. Examples are like social network or user item interaction network from e-commerce platform. These graphs are typically seen in industry level, and because they are so huge, we cannot store them in even a single machine CPU memory. So we need to partition it to multiple machines and using distributed training to achieve a machine learning task. So because there are 3 scales, in our hands-on part, we also break it into 3 sessions. In the first session, I will talk about some basic usage of DGL and how to build maybe your very first graph neural network model to solve some machine learning tasks on graphs. The later 2 sessions were about graphs of larger scale. 2 of my colleagues, Chuan and Da, will handle these respectively. For the second session, we will talk about how to train a graph neural network stochastically, which means instead of training on full graph, we sample substructures and train the GNN on that iteratively. And we will also cover how to further issue these samples to different GPUs so that we can use multi-GPU for further acceleration. The last session is about giant graphs, and Da will talk about how to use the distributed functionality in DGL to train these giant graphs on multiple machines. Okay, so for the first session, I will talk about some GNNs for basic graph tasks. Let's first look at the typical GNN workflow, where you will have a graph data, like what you see on your left-hand side, and a task you wish to perform on that graph data. Typical tasks are like node classification, where we want to predict labels or properties of each individual nodes. Link prediction, where we want to predict the existence of a certain links. Or graph classification, where we want to predict some properties of the whole graph. So given this graph data, the first step we typically do is to load that data and try to pre-process it and prepare the training and the testing sets. We then will build and train a GNN models to fulfill different downstream tasks. And these GNN models are very powerful tools which can be shared across different downstream tasks. To break down this pipeline, in this session, we will have several notebooks to cover different parts of this pipeline. So first of all, we'll have one notebook to cover how to load this data on disk into memory, pre-process it, pre-process some graph structure and feature data, prepare training and testing sets, and finally create a graph in DGL. The second notebook, 2GNN, will talk about how to create a graph neural network model using DGL, and how to train it to perform a node classification task. And the third one, we will reuse the model we just built, but instead of doing node classification, we apply it to a link prediction task. The idea is that we want to show the GNN models are very powerful tools that can be shared across different downstream tasks. And the graph we will use in all these 3 notebooks will be the Zachary's Karate Club network. So what is this network? So the network is like a social network where we have 34 nodes. Each node is a member of a karate club. And the links represents their interactions outside of club. So you can think about this as some kind of measure of their friendship. And during the study, an interesting thing happens. The group, the karate club, actually splits into two parts due to the conflict between the president and instructor of the karate club. And the goal is to predict for each member which group they join after split. And it is a typical community detection session because we wanted to detect the two different communities in this network based on only their interactions. Okay, so here is an overview of all our notebook. So I've already talked about like the 3 notebooks, 1, 2, 3, and also we have the 4th and 5th one. The 4th one, we will talk about how to use GPU to accelerate the training, and the 5th one is a more advanced session. We will talk about how to customize a GEM module by massively passing APIs in DGL. Okay, so let's begin. So here you can see a Jupyter Notebook interface. When you download the materials on our GitHub, you can see the same folder structure. So there will be a 3 basics folder, which is the session I led. And you can see there are 5 different notebooks here. So let's click the first one, load data. So for anyone who are not familiar with Jupyter Notebook, basically each notebook contains different cells, and each cell is like executable executable piece of code or some text describing what they are. And to run the notebook, you can click the kernel and either restart and clear all the outputs or restart and run all. So if you, for example, made some mistakes and you cannot go back, you can always click this kernel to run and restart everything. Okay, so in this notebook, we will talk about how to load and pre-process graph data. We'll talk about the load graph data stored in CSV file, construct the graph in DGL, query some structural information, and then prepare these edges and node and edge features. Okay, so perhaps all the data, the graph data is first stored on disk. So we need to first define what kind of formats we will use. So here in this tutorial, we use comma separated value CSV, which is a widely used format for storing relational data. Actually, we have prepared this CSV file that stored the Zachary's Karate Club network. There are 2 files. The nodes.csv stores every club members and their attributes, and there another one, edges.csv, stores the pairwise interactions between 2 club members. We can run the cell, and then you can see there are 2 CSV files. And to load these CSV files into memory, we can use pandas. And you can see here, this cell includes the codes for loading the node CSV into memory using pandas. And we can run it. And then you can see we printed out this node data. It's a table basically, and it has 3 columns. The first one is the ID of each node. The second one, club, has actually only 2 types of values, Mr. High and Officer. So these are the, you can think about it's like the club membership of each member after the split. And there are the third column edge, which is an integer feature for each club member. Similarly, we can also load this edges.csv using pandas, and then we can print it out. And you can see there are 156 rows because there are 156 edges in the graph. Similarly, if you look at the node data, you can see there are 34 rows because there are 34 members in the club. And for the edge table, you can see there are 3 columns as well. The first one, the second one are source and destination, representing the source node and destination node for each edge. And the third one, weight, is an edge attribute. It's a floating value indicating the strength of each edge. So we can construct a DGL graph from these 2 tables very easily. The idea is we first extract the source and the destination node arrays from the edges data. You can see we use edges source to get the arrays and convert it into NumPy. And similarly, we do so for depth arrays as well. And then we can call this DGL.graph and feed it as a pair, like source and destination node, to represent all the graph structure. And after that, we can print this graph to see some meta information. So let's run this cell. You can see it first say that, okay, we are using backend PyTorch. So note that DGL is a framework neutral package. You can use PyTorch, TensorFlow, and MXNet. It's DGL compatible, is compatible with all these 3. And for these tutorials, we will use PyTorch. And then you can see it prints out that, okay, the current backend is PyTorch. And if after we print the graph, you can see there are 34 nodes and 156 edges. And the N data and the E data schemes, we'll talk about that later. So this is a graph. G is basically a DGL graph. And a DGL graph can be converted to a network X graph very easily. So you can see here, we use this DGL.to network X, and it becomes a network X graph. And we know that network X is a very well-known package in Python that provides a rich functionality to perform analysis on graph data. So for example, here, we show that we can use network X to plot this graph so to have a better visualization. So let's run this code, and you can see it plots the graph very nicely. Okay, so now we have a graph. We want to know more about it, right? We want to know, okay, for example, how many edges, how many nodes are there in this graph. So DGL graph provides these APIs for you to do so. For example, here, you can see we have this number of nodes and number of edges API. We can run it, and it tells us that, okay, there are 34 nodes and 156 edges. And we can perform some more complicated queries like, okay, I want to get the degree of node 0. We can use this g.inDegrees API, and 0, and just the argument is just 0. And you can see it tells me that, okay, there are 16 nodes connected with this 0 nodes. And we can also get the successors of node 0 by g.successors. And you can see that it returns a tensor, integer tensor, containing the IDs of all the successors of node 0. In fact, these APIs are called graph query APIs. And DGL actually prefers a lot of these APIs for you to perform different kinds of graph queries, like the successor, predecessors, in degrees, out degrees, or finding adjacency neighbors. So you can always find this API document here by clicking this link. And these are very useful utilities if you want to perform some simple analysis tool, analysis on the graph. Okay, this is the graph structure. Let's talk about the node and edge features or attributes. So we know that in many graph data, nodes and edges have attributes. And they can have a rich type of values, like you can have timestamp for each node for all edges, or you can have some strings for username, so on and so forth. Although nodes and edges can have rich type in DGL, a DGL graph only accepts attributes stored in tensors, which means that these attributes must be numerical contents. And this is because DGL is a tool built for deep learning on graph, and the deep learning usually only handles numerical values. Therefore, in order to proceed, we need to convert these non-numerical values or attributes into numerical attributes. And there are typically different ways to do so. For example, here we just list a bunch of methods, like for categorical attributes like gender and occupation. You can consider converting them to integers or one-hot encoding. For variable and string contents like some articles, texts, or some quote, you can consider applying a language model so that the outcome is a fixed length vector for that encodes the string contents. And for images, it's very nature to use CNNs to convert the images to a high-level representation. For this particular example, remember we have these types of attributes. The age attribute is already an integer attribute, and so we can directly use it. The club is a categorical attribute. You can see here the club has two different types of values, Mr. High and an officer, meaning which group each member joins after the karate club split. And we need to convert these strings to categorical integers. And finally, there are weights on each edge, and they are floating numbers, so we can also directly use that. So here is how we do it. First of all, we get these edge features. For no data, we get these edge features out. You can see here, we convert it into NumPy, and we further convert it into touch tensor and perform some normalization so that the edge is within 0 and 1. So we can learn this. You can see we can run this. You can see here the outcome is a tensor. Each value is a floating value, and they're all from 0 to 1. And the good thing about this type of representation is that we have 34 nodes, and the tensor has also 34 entries, which means each entry is indeed the attribute, the edge attributes, or the edge feature of each node. Therefore, to get the features of a certain node, for example, here node 0, node 10, I can directly use the tensor slice. And you can see here, I slice, and given the indices of 0 and 10, and it print out 0 nodes and the 10th node's features, the edge feature. To set these features into the graph we just constructed, we could use this g.ndata syntax. So you can see here, g.ndata, I can feed this edge into G using this g.ndata. And the g.ndata is basically a dictionary-like interface. So you give it a name and you feed it to it. And then we can print it out this G, and you can see the ndata schemes here actually contains the ndata feature, a new ndata feature called age. And a scheme is basically tells you some meta information of this ndata. So here we know that the feature shape is a scalar, so it's empty. It's a scalar feature. And the data type of that feature is a floating 32, is a floated value. For the club feature, it's more complicated because the club is a string, right? So we need to convert it into 0 and 1 first. So here is how we do it. We first get a list of these club features. For the officer, we assign 1 for it, while for Mr. High, we assign 0 for it. So after that, this feature, club feature, is converted into 0, 1 tensor. And we can convert it into a PyTorch tensor. And to generate a one-hot encoding, we can use Torch's one-hot function to generate a one-hot encoding. And then we can print it out. To assign these features to the graph, we still use this g.ndata. And remember, g.ndata is a dictionary-like interface, so you can freely use this like update interface to do so. And here we demonstrate another usage of g.ndata. For example, this age, we don't actually use it. We don't actually need it. We can just delete it. And finally, we'll print out the graph and also the feature. You can see it here. The club is a one-hot encoding where the first is where each location meaning, okay, which category this node belongs to. And the graph has this E data where you can see club is still a scalar feature. Its data type is an integer 64. while the one hot club is a feature of is a vector feature of length 2, and the data type is still integer 64. And these are the node data. And for edge data, it's very similar. For edge data, you can use this E data syntax, G.E data, to do so. And you can see here, we first extract these weight features from the pandas table, convert it into PyTorch tensor, and then feed it into DGL. And then we can print out this G, and you can see here we also have an extra E data. Okay, so this is how we load the graph data from disk, do some pre-processing of the features, and also create a DGL graph, a graph object in DGL. Now we can click the second notebook to GNN. Let's look at some graph neural network. Yeah, okay. So here we will talk about how to build a graph neural network model to solve this karate club community detection problem. So here is another brief introduction of this Zachary's karate club problem. If you're interested, you can read that. And we will first try to see how can we formulate this problem as a semi-supervised node classification task, and then build a very popular graph neural network called the graph Sage, and train it and try to understand its outcome. Okay, let's first run this cell. It includes some necessary packages. And we need to understand this community detection problem. So community detection actually has a very long research history. So there are a lot of different methods proposed to solve this kind of problem. A lot of this approach is unsupervised, such as cluster, meaning that we don't see any labels, we just see the graph structure. And we want to predict the community labels by the connectivity. Recently, Thomas Kiff, who is also the author of graph convolution neural network, he proposed to formulate the community detection problem as a semi-supervised node classification task. That the idea is that apart from the connectivity, the model is also given a very small portion of the labeled nodes. And train the GNN using these teaching signals. And he shows that these GNNs can predict the community labels more accurately. So in this tutorial, we also apply the same setting to this Zachary's Karate Club networks to predict the community membership with only very few labels, actually only 2 labels. Okay, so we first load the graph and then know the labels. And since this has already been covered in the last session, we just provide you a function for loading the data. So you can run this cell. You can see that it loaded the Zachary network. It has 34 nodes and 156 edges. And there are 2 node data, the club membership in integer and the club 1 hot encoding. So the first thing we need to think about is how to assign features to this graph. We know that this is usually not a problem for real world or public data set because these features has already been there. But for this Zachary's Karate Club graph, we don't have any node features actually. So for featureless graphs, there are many ways to add features to the graph. And a common practice is to use an embedding matrix, where each node is assigned an embedding vector, and these embedding vectors are updated during the training together with the model parameters. And to do so, we can use PyTorch's embedding model to achieve this. So here is the code. You can see we call PyTorch's n.embedding, and the embedding size is number of nodes and 5, which means each node has an embedding of size 5. And we can initialize these embeddings using Xavier uniform, and we can print out the result. So here you can see this matrix is of shape 34 and 5. Each row represents the embedding vector of each node. And then we need to look at the labels. Remember, this is a semi-supervised setting, so we don't need to use all the labels. In fact, we only use 2 labels, node 0 and node 33, which are the president and the instructor of the karate club. And we use, and you can see we first query out the label tensors using this g.n data. And since we only use 0 and 33, so the label nodes are 0 and 33 list, and we can print out their labels. So we can run this cell, you can see the labels are 0 and 1. Okay, now we have all the inputs and the labels ready. We need to look at the models. So as Zizi and George has mentioned in the presentation, the core idea of graph neural network model is message passing, where we try to compute new node representations by aggregating neighbor informations. So you can see the equations we generally have 2 different equations. One is how we aggregate the neighbor informations. Another is how we incorporate these neighbor informations to generate a new node representation. So here, these are the equations for this graph stage model. So you can see the first one, for each node V, we look at its neighbors U and use an aggregate function, so to aggregate them. And the aggregate function can be summation, average, max, or min. And the second equation talks about how to incorporate these neighbor informations. So you can see here, we basically concatenate this neighbor information with the node feature of node V. We concatenate them and apply a linear transformation and an activation function. So in DGL, we actually have already provided a lot of implementations for popular neighbor aggregation modules, such as GraphSage. So you don't need to write, you don't need to implement them, and they can all be invoked easily with 1 line of codes. You can see the full list of supported graph convolution module here by clicking this link. So here is how we build a 2-layer GraphSage model using the SageConv module we just talked about. So this user experience is very similar to how you build a multi-layer perception or multi-layer CNN models in PyTorch. You can see in the init function, we define 2 different modules, the conv1, conv2, using the SageConv. We specify the feature dimensions and also the aggregation function, where we set to be average. In the forward function, we specify the computation logic of the forward propagation. And you can see there are 2 arguments to the forward function. The first one is the graph, the DGL graph itself. The second one is the input feature, where we initialized as a node embeddings. And we first go through the first convolution, apply a nonlinear transformation like RELU, and then apply another graph convolution. And finally, return the result. We can construct this or we can instantiate this graph sage model by this line of code and feed it with the correct size. For example, the first size should be 5 because it should be equal to the node embeddings we just created. And we specify 16 as the hidden layer size. The output should be 2 because we want to predict 2 classes, 0 and 1. And then to train this model, this part of a training loop is almost exactly the same as the typical training loop of PyTorch neural network model. So we first define the optimizer to be Adam, and then in the training loop, we train it for 100 epochs. We first perform forward propagation, where the inputs is the node embeddings we define, and the graph is the saturated graph we just loaded, get some output logics. And for the loss function, since this is a node classification, we use cross entropy. And one thing to note that because this is a semi-supervised training, we don't use all the labels as a supervision signal. So here you can see we only use the labels of the label nodes, which is 0 and 33. We compute the loss and perform the backward propagation by calling loss.backward, optimization.step, and that finish the training loop. So we can run these definitions. And you can see that the model trains very quickly, the loss drops very fast. And we can verify the results by checking this accuracy. And you can see that the accuracy is not bad. Although sometimes you will see the accuracy is quite poor for this example. This is because the setting is pretty hard since we only have two labels, 0 and 1. So there are many variants for this toy task, and we didn't tune it very thoroughly. So maybe you can run this notebook several times. You can see that sometimes the accuracy will be pretty good. Okay. So this is how we implement this graph neural network and how to train it on Zachary Karate Club network to perform a community detection task. But we want to further understand the results. So remember, the task is to actually predict two classes, right? Like each class, the two classes, 0 and 1, and which means the output logis here is a two-dimensional vector for each node. And because it's a two-dimensional, it's a vector of two elements, we can plot that vector into a 2D plan. So this is how we do it. You can see here, this is a visualization of this outcome logits. Each point here, you can see the label here is the node ID, and we plot it according to its logits. And this plot is from the epoch 0, and you can see here the red nodes and the blue nodes, which are of different labels, are actually mixed together. And during the training, here is animation, and you can see that during the training, the model learns how to separate these red nodes and the blue nodes into compact groups, so that the final classification layer can classify these nodes very easily. I also provide this code for visualizing the result here. You can run this code. It takes a while and to generate a video, and it requires FFmpeg. Okay, so here you can see this is the animation. Yeah, you can see like in the first epoch, the nodes are mixed. The different classes are mixed together, entangled together. It's very hard to classify them. But during the training, the model successfully separates them into two parts. So it's easier to classify them. So some small exercises. You can follow the instruction in this notebook. You can play with more GN models, replacing, for example, the graphs, the SageConv model, the SageConv module with other graph convolution modules, and to see what happens. Okay, so this is second notebook. Let's click the third one, link predict. So here in this tutorial, we try to demonstrate that, okay, GNNs are powerful tools that can be reused in different downstream tasks. And we still use this Zachary Karate Club graph, but instead of doing community detection, we reformulated as a link prediction task. So in this tutorial, we'll learn how to prepare training and the testing sets for a link prediction task, and how to build a GN-based link prediction model, and how to train it and verify the results. Let's first run the first cell. Again, we load the data and also initialize the node features as we have done before. Okay, you can see the graph is successfully loaded. 34 nodes and 156 edges with some club information. And this is the initial feature of initial embedding for each node. Now we need to prepare the training and testing set for link prediction. So in generally, a link prediction task data set contains two types of edges, positive edges and negative edges. The goal is that we want to predict high scores for positive edges, but while predict low scores for negative edges. So we separate them, and the model needs to distinguish them very clearly. So for positive edges, it's very easy because all the edges in this graph is positive edges. And here in this example, we just randomly pick 50 edges for testing and leave the rest for training. So you can see here is the code how to make the positive edges. We first use this g.edges API to get all the edges in two pair of tensors U and V. And then we generate these EIDs. Remember, all the node and edges in DGL graph is labeled from 0 to the number of nodes or number of edges. So we can just directly generate the all the edge IDs using this arrange function. We permutate it randomly and then pick 50 for test set and the rest for the training set. Okay, we run this, and here we have this positive training, positive data set, and positive edges. And for negative edges, it's a little bit more trickier. This is because the number of negative edges is usually huge, and because the graph is very sparse. So in real world cases, negative sampling is very needed because there are just too many negative edges. And how to choose proper negative sampling algorithm is actually a widely studied topic, and we won't cover that in this tutorial. So for this particular example, since the graph is so small, like this karate club only have 34 nodes, we can actually enumerate all the missing edges and treat them as negative edges. So here we pick 50 for testing and 150 for training. So here's the code to do so. You can see here we use this U and V edge tensors generated previously. We create a sparse tensor, sparse matrix representing the adjacency matrix of this graph, and we negate it to find all the negative edges. And finally, we pick 50 for the test set and 150 for the training set. So let's run this code. And finally, we can concatenate all the positive and the negative edges to form the training and testing set. Okay. Now we have the training and testing set. How about the models? In fact, the graph we can directly reuse the graph sage model we defined previously for node classification. And you can see here, this is how we do it. We first, again, create two convolution modules, conv1 and conv2. And in the forward function, we go through each convolution modules one by one, and also the nonlinear function. And finally, we create a network. So the different thing is about the loss function. And here we use this dot product as one way to compute the loss function. So the idea is that since the graph neural network model has already given us a very nice node representation of each node because it aggregates the neighbor information, to predict the score for each edge, we just use a dot product of the node representations, and then use a nonlinear function, and then use a sigmoid function to cast it into 0 and 1. And for the loss function, we just use a binary cross entropy so that for positive edges, we want to predict 1 as much as possible, while for negative edges, we predict 0 as much as possible. So here is the code. You can see the optimizer we define here. And in the forward pass, we still go through the same graph sage network, get the lodges for each node, And then we use this slice operation to find the to do the dot product and generate the scores for each edge, go through a sigmoid to cast it into 0 and 1, and finally apply a binary cross entropy. And the backward is the same, using backward and step, and that completes the whole training loop. And we can run this one by one. Like run this one first, run the training loop, and you can see the loss drops very quickly. And then we can check the result. You can see the accuracy is pretty high because there are a lot of actually edges, and we can predict the edges correctly, like almost 90% of the accuracy. So here you can see this is a complete example of using graph neural network for link prediction. And it shows that we can actually encode the graph or learn the node representation, use the same graph neural network model, and we just need to simply change the loss function for different downstream tasks. Okay, now you can see that we have gone through 3 notebooks. The first one talk about how to load the data and create a graph object in DGL. And second one, the third one are building graph neural networks for different downstream tasks, so classification and link prediction. And the fourth one, let's click the first one. The first one, let's switch the topic a little bit. Let's see how can we speed up the training using GPUs. So in this tutorial, we'll learn how to copy the graph and the feature data to GPU and train that model on GPUs too. So again, let's run the first cell to include some necessary packages, load the graph. Okay, so the graph, you can see the graph has been loaded. And once it is loaded, it is currently still in CPU. And to copy the graph and its features to GPU, we can use these 2 API to copy them. And we can run this cell. You can see that originally the device is on CPU. You can use this g.device property to look at the device information of that graph. And then we copy that graph to GPU, which will return a new graph on a different context. So here the device is CUDA0, meaning the first GPU card, and then the new device become CUDA0. And this 2 operation copies not only the graph structure, but also the feature data. So we can verify that by looking at the feature data, the node feature data club and the club 1 hard by looking at their device. So you can see here, the device all prints out to be CUDA0. And to train a graph neural net model on GPU, the step is actually the same as creating a CNN or RNN model on GPU using regular PyTorch. You can use the 2 API to do so. So here you can see we created the node embedding as before, but instead of directly initialize it, we cast it or copy it to GPU using this 2, and then we initialize it as before. So you can see when after we initialize it, the parameters is on CUDA device. And the labels are the same. You can see here, because the labels are already on CUDA, slicing it also giving the CUDA tensor. And for the graph neural network model, it's the same. We first define the graph neural network model as before. And then to copy it to GPU, we just use these 2 API. So you can see here, this net.2 CUDA0 will return a new graph neural network model that is on GPU. We run it, and then you can see the training loop is exactly the same since we didn't change anything. And we run it, and it trains smoothly. And then we can verify the results. Yes. So this tutorial, we talk about, in this notebook, we talk about how to copy the whole graph and the feature data to GPU for training. So GPU is much faster on CPU, so you can train it potentially much faster. But you might have some questions, like, okay, what if the graph and its feature data cannot fit into 1 GPU memory? So what can we do? So basically, there are several ideas here. So instead of running a GNN on the full graph, we can run it on some sampled subgraphs to converge. You can think about we run it iteratively on different samples, while each sample is much smaller, so we can put it on GPU. And we can potentially issue different samples to different GPUs to enjoy even more acceleration. And for graph that is very, very large, we can partition the graph to multiple machines and then train it distributedly. So this will be covered in the later sessions by Juan and Da. So hopefully you will stay with us there as well. Okay, for the final notebook, I want to briefly talk about some advanced usage of DGL. So this notebook is mostly about how to customize, how to write your own graph convolution module using the message passing APIs in DGL. So we know, so in the previous sessions, you can see that we all use the built-in, like the provided modules in DGL to build graph neural models. But we know that a lot of researchers wanted to invent their own graph neural network modules. So how can we do that? And this is what this notebook is for. We will introduce the message passing APIs for you to write new convolution modules. So here, let's first run this cell and get some input. Let's look at the implementation of this graph sage in DGL. So remember, we have two equations. The first one is for neighbor aggregation. The second one is to incorporate the neighbor information and its own features to generate a new node representation. So here is how we define a sage count module in DGL. So you can see here in the init function, we initialize a linear transformation, which is the W, the trainable parameter W here. The core part is actually in the forward function. This g.update all is called the message passing API in DGL. It essentially performs the node aggregation, the first equation for graph sage in the graph sage definition. So there are three concepts here. So the first argument is the message function called, you can see here we import DGL function, and this function is provided by DGL called copy U. It essentially means that, okay, how the messages is generated. It is generated by copy the edge feature of node view, which meaning the source node of the source nodes, and then generate a message named M. And the second argument is a reduce function. And here you can see the reduce function is called f.min. So which means, okay, I will average all the received messages. And the messages are from name M. And after we average the messages, we generate a new node representation called HNATE. So this g.update all tells DGL that, okay, I wanted to trigger this message and reduce for all the nodes and edges. So after we call this update all, you can see we can now get a new feature called HNATE from this N data, HNATE. So this is the average, the neighbor representation for each node. And to implement the next equation, it's very straightforward. We just concatenate H and HNATE on their feature dimension. We got H total. And then we apply the W, which is the linear module we defined in the init function, and apply a IERU nonlinearity. So this is how we implement a sage count module in DGL. And actually, we can, in DGL, we provide not only this copy U and the min function for message and reduce function, we provide many different combinations. And they are all in the scope of message passing APIs. Essentially, the message passing APIs has these equations, very general equations. The first one is try to compute the messages flow from node U to node V. You can see it has three inputs. The source node and destination node feature, and also the edge data. And this M function is customizable. So in this, in the above example with this copy U, and then is the aggregation, the message aggregation. Here, the sigma is not necessarily summation, can be other reduction functions like averaging or max or min. And finally, the update function will take care of how to merge the messages received with its own node embeddings. So in DGL, the DGL.function packages includes all the built-in messenger reduce function provided by DGL. So you can see here we have a bunch of different ones like copy U or copy E, and also we have binary message functions, which means you can perform some more complicated operations during the message computation. So here you can see we have this like a U add V, meaning okay, I will add the U the source node feature with the destination node feature. And let's see an example. So here we try to have a new SageConf module, we wanted to incorporate the edge weight during the message propagation. So this is a very common case since a lot of times your graph have weights on each edge, indicating the strength of each link. So how can we incorporate it? You can see here we besides like adding this node feature edge into g.n data, we also adding this W, meaning the edge weight into g.e data. And here we just change the message function from fn.copyU to u mod e, meaning that, okay, I wanted to multiply the edge feature of the source nodes with the W feature on the edges and produce a message named M. And the reduce function is the same. We average them and produce a new node representation called HNA. And we get this HNA, we concatenate them with each node's original features as before, and then apply the nonlinear function. So you can see here, changing this SageConf module to have a new one is very easy. And this g.updateAll syntax is also quite succinct, quite similar to your mathematical definition. So we have talked about how to customize a graph convolution module using DGL's built-in message reduce function. And you might wonder, okay, what if my neural network is very, very complicated? It just went out of scope of the provided functionality. So in DGL, we also have a more advanced way to customize your message reduce function called the user-defined function. So here is an example. You can see if we want to implement our own u mod e, we can use a native Python function here. So we just define a Python function u mod e udf, and the argument edges, meaning a batch of edges, and also contains the data of each edge. So you can see here, we get the source node data edge and multiply it with the destination node data W. Sorry, not destination node data, but the edge data W. And the result is a dictionary. I return a dictionary of messages and give it a name as an M. So this is exactly this. This actually implements exactly same logic as our fn.u mod e, and you can just replace this use this u mod e udf here in the first argument of update all, and everything should work fine. So the difference of the UDF is the built-in function is that in DGL, we recommend you to use UDF, we recommend you to use the built-in function as much as possible. Since they are more efficient, we will actually internally mapping these built-in functions to very efficient GPU kernels. While for UDF, since it is defined in Python, we need to adopt some strategies to run it, but it is not as efficient as the built-in function. So try to use the built-in functions as much as possible. But UDF is still very good for quick prototyping if your graph is not small. Is small. Okay, so some recap. In this notebook, we talk about that, okay, DGL.N provides many popular modules for quick bootstrap. And we can use the built-in message reduce function in the DGL.Function package to customize a new GN model. And you can further perform customization using the user-defined functions. Okay, that completes my session. So if you have any questions, as I have mentioned before, please join our Slack channel here, scan this QR code. We are happy to answer any of your questions. And for all the model and the tutorial contents, you can find them at this GitHub link. So thanks, everyone.
Okay, so this is this morning's tutorial. So I think now, according to our schedule, now we are going to have a lunch break. But if anyone has any questions about the first hands-on tutorial, I think we can continue discuss. So is there any, are there any more questions? So if not, let's have a 1 hour break, and then we can. So for anyone who is in US, we can go to lunch, and then we will come back later and start our next session at 1 p.m. Pacific time. So see you guys in 1 hour.
Okay, so let's get started. Can you guys hear me? And can you guys see my screen? All right, cool. So this tutorial would be about training a graph neural network with DGR on a large graph. For now, I will talk about training a model for node classification and link prediction with a single machine with one or more GPUs. So by large graph, I mean the graph whose structure or node and edge features cannot fit into a single GPU memory. So this tutorial would be about training on a large graph with limited amount of GPU memory. The tutorial of training with a cluster with multiple machines will come next. Sorry. So in real world, especially for industrial business data, we often have a graph with millions or billions of nodes and edges. For instance, knowledge graphs such as Freebase often have millions of nodes and billions of triplets, and social networks or recommender system datasets often have billions of nodes or interactions. So in the last tutorial, we briefly learned how to write a graph neural network with full graph training, and that technique only works on smaller graphs. For million node or billion node graphs, the node features almost certainly cannot fit into the GPU. Sometimes it cannot even host memory on a single machine. So we need to borrow the idea from stochastic training in traditional deep learning approaches, such as those in the computer vision or natural language processing. So before going deep into the stochastic training of graph neural networks, let's have a recap on how stochastic training works on computer vision or natural language processing. In those fields, we often have a data set of examples as well as the labels. And for each gradient step, we only select a small subset of the examples and then compute the losses from those examples only. And then we compute the gradients and do the backpropagation and update the deep learning model parameters. So the mini-batch training technique does not directly apply to graph neural networks because the representation of the node would depend on the representation of other nodes on the previous layers. So we can look at the graph stage model as an example. So we can see that the representation of the node computed by a multi-layer GNN that not only depends on the input feature of that node, but also that of the neighboring nodes, and maybe the neighboring nodes of the neighboring nodes for the last third layer, and maybe the neighboring nodes of the neighboring nodes of the neighboring nodes when the graph stage model gets deeper, so on and so forth. So here's a concrete example of computing the representation of node 1, which is called blue, with a 2-layer graph stage. So we obviously need the first layer so to compute the second layer representation of the blue node, we certainly need the first layer representation of the blue node 1, and also the first layer representation of all the neighbors of the blue node, which is colored red here. So to compute the first layer representation of the blue node and the green and the red nodes, let's say for node 2, we will need the input feature for the node 2 and node 1, which is colored orange. And the same goes on for node 3, which needs the input feature of the red node and the orange nodes. And similarly for node 4 and node 5 and node 6. So if we draw down the entire computation dependency of the second layer representation of node 1, which is the blue node here, we can see that it actually depends on a lot more other nodes for the input feature. So in this case, we will have the blue node the second layer representation of node 1 would actually depend on 9 nodes for the input features. So in stochastic training of graph neural networks, we not only need to load the input features from the subset of the nodes, we selected to compute the loss. We also need to load the input features from the neighbors, and if necessary, the neighbors of neighbors, maybe neighbors of neighbors of neighbors, and so on and so forth. And doing this naively will often lead us to too many nodes. So this is actually more prominent on the graphs that obey the so-called power law, meaning that the degree of the nodes will follow a power law distribution. And usually those graphs are, the diameters of those graphs are often very small and oftentimes constant, regardless of the number of nodes you have in the graph. So in those cases, even a two-layer GNN will often end up in, depending on input features of from a large portion of the entire graph. So we will find ways to actually prune the dependencies so that we don't depend on that many features, so we can fit the training process into GPU memory. So there are various ways to prune the computation dependency. From the first session, we know we know the strategy called neighbor sampling, and there are also other approaches such as VRGCN and also layer-wise sampling, which is essentially sampling a constant number of nodes for each layer, and also random walk-based sampling such as PinSage, and also subgraph sampling, such as those the models such as cluster GCN and GraphSync. So in this tutorial, we will only talk about the neighbor sampling. Although in DGO, we also have ways to write your custom neighborhood or subgraph sampler, which we'll briefly mention it in the hands-on tutorials. So the idea of neighbor sampling is simple. When we aggregate message from the neighbors, previously, we are trying to aggregate message from for a node from all the neighbors. But with neighbor sampling, we will only select a small fixed number of neighbors for each node. So in this example, if we decide to only gather messages from 2 neighbors, the resulting computation dependency will be much smaller. So in this case, the blue node will only depend on 3 nodes, which is more affordable. So I've seen someone asking where we can find the slides of the presentation. So the presentation should be available on the GitHub repository. If not, then I will update it. So the overall stochastic training of the GNNs will then go as the following. So first, we pick a subset of the nodes to compute the losses on. Then we figure out the computation dependency with neighbor sampling or other sampling approaches. And then finally, we pass the computation dependency into the graph neural network. So in this case, we will compute the first layer representation of node 2 and node 4 based on the node representation 1, 7, and 8, called orange. And after we obtain the first layer representation of the red nodes, we will compute the blue node, which is the node we sampled in this mini batch, based on the first layer representation of the red nodes. And after that, we compute the loss function, and then we do the backpropagation as usually we do in training other deep learning models. So far is the overview of the stochastic training process. And next, we will see how we can write graph neural networks in DGO for stochastic training. Before that, I would like to ask if you have any questions. If not, we can directly proceed to the notebooks. Okay, so let's move on to the notebook. So the first notebook would be about writing a stochastic training procedure for GNS for node classification. So in this tutorial, you will learn how to do node classification with a multi-layer GraphSage. And the dataset we choose is Amazon Co-Purchase Network, which is a standard OGB dataset. For OGB, you can Google for the Open Graph benchmark to see the comprehensive list of the all the data set they provide, and the coverage of their data set is includes the various node classification tasks and link prediction tasks and graph classification tasks. So for Amazon co-purchase network dataset, it contains 2.4 million nodes and 61 million edges, and that graph cannot fit. That graph obviously cannot fit into a single GPU. So the contents in this tutorial would include how to create your DGL graph from your own data in other formats, such as CSV, and also training a GNN model with a single machine with a single GPU with on a graph of any number of nodes and edges. So first we download the data set. Although you can directly use the Python package provided by OGB, for demonstration, we are actually manually downloading the data set from the S3 bucket because apparently we have like 30 or 40 people watching this tutorial. And if we download this OGB product data set at the same time, it will probably overload the OGB server. So we are instead downloading this from our S3 bucket. But they are the same data set. So after we download it, we unzip, we unpack it, and then we can find the data set containing the following files. So the first one is the edge.csv containing the source destination pairs. And the second one, third one contains the node features and node labels, which are, so the node feature is a fixed dimension vector, dense vector. And the node label would consist of a single integer indicating the category of the node. For the last two CSV files, we're not going to use it. In addition, it also contains the following files, which is train.csv, valid.csv, and test.csv. These three files contain the training, validation, test split for the data set. So here we are trying to load the data sets using pandas, and so essentially we're loading the three CSV files containing the graph structure and node features using pandas, and also the training validation test set with pandas. And then after we do load the graph from the CSV files and do some pre-processing, we can save the constructed DGL graph project, DGL graph object with as well as the node features and node labels with pickle. So you can simply just do pickle.dump, and that will save the graph onto the disk. And after that, you can just load the graph back from the file we saved. So here you will be just opening the pickle file we previously saved, and then we load the graph and node features and training validation test split from the from the pickle file we have just created. So someone is asking why we want to save to the disk. So here it's just a demonstration of saying that you can simply save the DGL graph object onto the disk, and usually when you actually do GNN training, you will be oftentimes first do some pre-processing, like dropping some noisy edges or do some data cleanup, and then you construct a DGL graph object, and you can just save it onto the disk as so that you don't have to pre-process the data set every time you train it. So after we load the data, we can see the size of the graph, features, and labels using the print statements. And you can see there's like almost 2.5 million nodes and 62 million edges. And the node features are have 100 dimensions, and the number of classes is 47. So after we load the graph, we are now trying to define a data loader with neighbor sampling. So the data loader is essentially the tool PyTorch provides us for doing mini batch training, which iterates over the data set in mini batches. So the DGO's data loader has a similar concept. So before we actually go to the implementation of how to create a data loader, let's first do a brief overview on the neighbor sampling. So for instance, if you want to do you want to perform the message passing for updating red node on this graph, you will need to send messages from the green nodes and along the edges, along the arrows drawn in the following figure. So if we are trying to compute the red node's second layer representation, we will need the first layer representation of the green and red node, and also the input of the green, red nodes, as well as the yellow nodes. This is similar to what we have seen in the slides before. And from that, you can see that computing the representation from even for a small number of nodes will resulting requiring input features of a significantly larger number of nodes. And that's why we do neighbor sampling, which shrinks down the number of nodes needed for inputs. So in this case, we will only have 2 green nodes and also 4 yellow nodes here. But note that this is only a simple realization, like one of the many realization of the neighbor sampling. It can also the message passing directions can also the edges involved in message passing can also change in different iterations, because we may as well select other subsets of the neighbors. So DGO will provide useful tools to generate the computation dependency we need. The primary tools DGO provides is this node data loader class and the multi-layer neighbor sampler class. So the syntax of node data loader is mostly similar to a PyTorch data loader, except that you need to specify a graph and also a set of node IDs to iterate on, and also the neighbor sampler you specify. So let's consider training as 3-layer graph stage, and you will sample each node. You will sample 4 neighbors for each node on each layer. So the code for creating the data loader and neighbor sampler will look like this. So first, you specify the strategy of doing neighborhood sampling using this multi-layer neighbor sampler, which is essentially randomly picking 4 neighbors uniformly. And then you create the data loader using this node data loader class, which specifies the graph, the set of node IDs in the training set, and neighbor sampler. The rest of the arguments are exactly the same as PyTorch data loader. So essentially, we're iterating in size of 1024 nodes, and we shuffle the data. We shuffle the node set, and here we are not using multiple worker processes to do the sampling. So after that, we can iterate over the data loader and see what it gives us. So essentially, so node data loader usually will give us 3 items per iteration. The first one is the input node list. which means that to compute the representation of the nodes in the mini batch from the final layer, we will need input features from these nodes. The output node list will the second item is the output node list, which is essentially the nodes we sampled in this mini batch, and the representation will be computed for this mini batch. The last item is the list of computation dependency for each layer, which is identified as a block in DGL. So here we will just check like how many nodes we need, how many nodes input features are needed to compute this mini batch. And the blocks here shows how message will aggregate on each layer. So essentially, this output tells us that the first layer would require this many input nodes, and the output nodes will have this number. The first layer will compute the output representation for this number of nodes, and the second layer will take in this number of nodes and compute the output for this number of nodes, and so on and so forth. And also each block will have the dependency encoded that shows how input features will how input features will send messages to how input nodes will send messages to the output nodes. So after this, we will be defining the model. So after we define the data loader, we are going to define a model. So here we can see that the graph stage model we define here is quite similar to the graph stage model we have seen in the previous tutorial session. We'll be initializing with a PyTorch module list, and then we add this number of SageConv modules, which is provided by DGL for graph stage convolution. And the forward propagation simply involves iterating over the pair of layers and the blocks. Blocks is essentially this thing, like the list of computation dependency yielded by the data loader. So we iterate over the pair of layers and blocks, and then we feed the block into the layer, and as well as the input feature, and it will automatically give us the output feature from this layer. And if the layer is not a final layer, we pass it with a reload activation. So after that, we are going to define a training loop. So to initialize the model simply involves initializing the graph stage model we created above. And we specify the input feature as the variable num features, which is 100. And also the hidden feature would be 128. Number of classes, and 3 is essentially the number of layers. And then once we initialize the model, we copy it into the GPU using CUDA, the CUDA method. And then we create the optimizer. So usually when we do computation, when we compute the validation score for model selection, we can also usually we can also do neighbor sampling. The reason is that the validation set is often very small compared to the size of the graph itself. And also it's usually okay-ish if we introduce some kind of randomness into validation score computation for model selection. So to do that, you simply need to define another data loader, which we call validator loader here, but the code is essentially the same as how we define the train data loader, except that we are using another node ID set. So the following would be a training loop that performs validation every epoch. So essentially, we first set the model as the training mode, and then we iterate over the train data loader. TQDM is the tool that displays a progress bar in the console or in the Jupyter notebook. So we iterate over the data loader, and once we have the input nodes and output nodes and the blocks, which is the list of computation dependency, we first copy this dependency, which itself is also a graph, to the GPU using this list comprehension, and then we load the input features and the output labels, and then we copy them to GPU. After that, we simply feed the list of blocks and the input features into the model, and then we get the predictions. So after we get the predictions, we compare it with labels to compute the cross entropy, and then we do back propagation as well as the model parameter updates. And once we finished iterating over the training set, we then iterate over the validation set, and then we compute the validation accuracy using essentially the same code, except that we will be predicting the category using this argmax function, which outputs the indices with the largest values. So once you execute it, it will be automatically do the training and then do the validation. It will also save the best model by comparing the validation accuracy you have seen so far with the best accuracy, or with the current accuracy. Sorry. So I guess I will interrupt it. So so much for training and validation. But for offline inference, we often find it desirable to aggregate over the entire neighborhood to eliminate randomness. But usually using the same methodology as above is not very efficient, because we're aggregating over the entire neighborhood. Usually, even computing a single node will often require a large number of input nodes. And also there will be a lot of redundant computation. So instead, we will need to compute the representations layer by layer. And for each layer, we will be iterating over the nodes in mini batches. So essentially, you can see the computation procedure with this animation. So essentially, you first iterate so essentially you start by computing all the nodes for the first layer. And for the first layer, iterate over the nodes in mini batches. In this case, we will iterate over 2 nodes at a time. So after we finish computing all the nodes on the first layer, we then move on to the second layer, and so on and so forth. So here is how we implement the offline inference we have discussed above. So here we will be using this multi-layer neighbor sampler, which has a none as the input, which means that we'll be using all the neighborhood, and we will only iterate over 1 layer at a time. So the length of the input is 1. And the data loader is essentially the same as the train data loader and validation data loader. And here we'll have a 2-level loop. The outer loop would be iterating over the layers, and the output feature. So here we first allocate a buffer that will be ready to store the output representations for the current layer for all the nodes, and then we iterate over the nodes in mini batches, and then we compute the representation of output representation of that mini batch for the current layer. And once we compute that, we write back the output features into we computed into this buffer at the indices yielded by the data loader. And if we finish once we finish the iterating over the node set, we will move on to the next layer, and then after we finish all the layers, we will simply have the output representation for the final layer for all the nodes. So oops, forgot to run it. So this cell would simply load the best model we have seen so far, and then we perform offline inference. So it will also compute the accuracy on the test set in this cell. So with this technique, you can simply do training and validation for a graph of any number of nodes and for any number of nodes and edges, and you can also do offline inference, which computes the exact neighborhood exact message passing result for a graph with any size. The primary technique we introduced here is doing mini batch and using node data loader and multi-layer neighbor sampler to do mini batch iteration. So in this notebook, you have learned how to train a multi-layer graph stage with neighbor sampling, and the next notebook will be about how to do graph stage in an unsupervised manner with link prediction. So before we move on, any questions so far? So someone is asking why only apply ReLU to non-last layer here. So if we apply ReLU to the last layer, because for classification, we will oftentimes compute the cross entropy, which is essentially computing the softmax from the final layer's output, and we use the softmax output as a probability. If we apply ReLU to the non-last layer, then if we apply ReLU to the last layer, then for the negative values, it will essentially truncate to 0, and essentially the softmax input will be always non-negative, and usually that hurts the performance a lot. So did that answer your question? Okay, cool. So any other questions? Oh, so what type of instance do we need to train a model like this one? So do you mean, so by instance, do you mean something like AWS instance, or like what kind of machine do you need? Oh, AWS instance. So so here we are using a GPU instance. So for the SageMaker notebook you created, I believe it's either P2 or P3. Although you can technically use any kind of GPU machines, any machines that uses GPU. All right. So any other questions?
I have a question. Can you hear me?
Sure.
So here it seems like we still load all the data into memory, right?
I'm sorry?
So here it seems like before we train the model, we still, loaded all the data, training data into memory. Is that true?
Right, but it's CPU memory instead of GPU memory.
Okay, but like what's the interface, or do we have interface when the data is too big to load entirely into the memory?
So if the data is not able to fit into a single machine, even for CPU memory, it will be in the scope of distributed training, which will be in the next session, next session given by Da. So
okay.
Here we'll only talk about how to when the graph is able to fit into a single machine CPU memory, but not GPU memory.
I see. Okay, so here we're assuming the graph can be fitted into a single machine.
Right.
I guess the difficult part is for the graph, because for data, you have the similar data loader like PyTorch. You can read, file from disk, right? If the file input data is too large. Well, I mean, I guess the data here is the graph itself. Okay, I see.
Yeah.
Okay, thanks.
No problem. So I guess we can move on to the next notebook, which will be about stochastic training for link prediction. So although the title is called link prediction, it also tells you how to do unsupervised learning with GraphSage, how we usually do unsupervised learning with graph neural networks. So here the data set is still the Amazon co-purchase network, same as the one in the previous notebook. But here we will be training a multi-layer GNN model for unsupervised in an unsupervised learning setting, meaning that we are not gonna use the labels and we are only trying to learn the node representation of the nodes. So here, so the notebook will contain the material necessary for training a GNN model for link prediction or unsupervised learning with mini-batch training. So here's a brief overview of how we usually do link prediction. So essentially, essentially involves two stages. One is to so the objective of link prediction is to essentially predict whether an edge exists between two given nodes or not. So we often just formulate the problem as predicting a score of an edge of a score between two nodes. So first we get the representation of the two nodes we're considering using the graph neural network. And after that, we will pass the two nodes representations into another function to compute a scalar score indicating the likelihood of an edge existing between the two nodes or not. And we usually train the model using negative sampling, which is essentially comparing two nodes that has a real edge connecting between them against the other pair of nodes where an edge doesn't exist. So a common loss function is negative log likelihood, which is written in this formulation. But other loss functions such as VPR or margin loss can also be used. So if you work on recommendation or word embedding learning, you will find the formulation very similar to implicit matrix factorization or that in word embedding learning. So link prediction is already quite useful in recommendation, where you will predict essentially you will predict whether a user will interact with another with an item if we consider the users and items as nodes. But it's also useful in unsupervised learning setting, where the node labels are not available or you don't plan to use it, and you just want to learn a latent representation of all the nodes. So essentially here we will train the model by predicting whether two nodes are connected with an edge. And after the model is trained, the learned representation can be used later for either, let's say, nearest neighbor search or future training of a more simple classifier, or we can treat the GNN as, we can treat this process as a kind of pre-training step on this graph. So the objective function can also be combined together with supervised cross-entropy loss for node classifications. So here, this cell will be simply loaded in a data set, which is created by the previous notebook. And then we will be similarly defining data loader with neighbor sampling. So for link prediction, DGL provides this edge data loader that iterates over the edges for edge classification or link prediction tasks. So in particular, if you want to do link prediction, you will need to provide a negative sampler. So the signature of the negative sampler is essentially it has two arguments called, one is the graph and another is the edge ID tensor, and returns a pair of tensors. The pair of tensors is essentially the negative example, negative pairs to be compared with the edge IDs. So this code will implement a negative sampler, and the negative samples are generated by corrupting the destination node with a distribution which is proportional to the power of the integrity. And this formulation is used in the official GraphSage implementation given by the authors. So after we define a negative sampler, we can define the edge data loader with neighbor sampling. So here's an example of creating a data loader for link prediction with each positive example associated with five negative examples. So here we'll use the same neighbor sampling strategy. Essentially, each node will sample 4 neighbors for each layer, and we are training a 3-layer graph neural network. And the trained data loader would be iterating over the edges, and the negative sampler is essentially the one we created above. And the rest of the arguments are essentially the same as the PyTorch data loader. So we can look into how what the trained data loader gives us. So essentially it will give us 4 elements. The first one is the input node list, and the second one is essentially a graph consisting of all the nodes, but consisting of all the edges sampled in this mini batch. The third item is the graph consisting of all the negative pairs as edges sampled in the mini batch. And the last one is the list of blocks, which is the same as which has the same meaning as the one we have seen in the previous session. So this is essentially checking how many input nodes we need for computing this mini batch, and how many edges we have in this in this graph with all the positive edges, and how many edges we have in this graph with negative edges. And this is the computation dependency list for each graph neural network layer. So the model, so the GraphSage model implementation is essentially the same, exactly the same as the one in the previous tutorial session. And here the offline inference is also exactly the same as the one we have seen before. So the difference starts from here, where we will be predicting the score of an edge. And the way to predict the score of the edges will go like this. So essentially, we start with a subgraph, which is either the positive graph or negative graph we created above, that consists of the positive edges or negative edges only. And also X. X is essentially the output nodes, output features given by the graph neural network above. So here we'll use this apply edges function that computes the dot product, and this function is essentially saying that we will be computing the dot product between the output representation of the source node and destination node. And we use the dot product as the likelihood of whether the edge exists between these two nodes or not. So this is the score predictor that predicts the likelihood of the edge's existence. So to evaluate the performance of the learned embedding, we usually have we have a lot of ways to do that. We can either do nearest neighbor search, and in the original GraphSage paper, they are training a simple linear classifier of based on the learned node embedding, and also the original training and validation test split. And they train a linear classifier on the training set with the learned node embedding, and then evaluate it on the test set. And they use the validation, they use the test accuracy to determine whether the learned embedding is good or not. So here we are staying loyal to the official implementation. So here's the training loop. So the training loop is essentially instantiating the GraphSage, a 3-layer GraphSage model as we have seen before. And also, in addition, we will also have this score predictor module, which is essentially predicting the likelihood of the edges existence. And then we create the optimizer, which includes both the parameters of the GNN model and the score predictor. And the following cell is essentially the training loop for unsupervised learning and evaluation. So the difference is, so the difference is starts from here. So here is the same as the, so this one is the same as the node classification, where we copy the list of blocks onto the GPU for message passing with the GNN we created. And this positive graph is the subgraph consisting of the positive edges, and negative graph is the graph consisting of the negative edges only. So we load the input features, and then we compute the outputs, compute the features of the output nodes from the given by the last layer, and then we feed the outputs into the score predictor model we created before. So if we give the positive graph to the score predictor with the outputs, we get the positive score, which is essentially the likelihood for all the positive edges we sampled in the mini batch. And next score is we can get the next score from by giving the negative graph into the score predictor. And this will give us the likelihood for all the negative examples. And then here we are essentially assigning the positive edges with the label 1 and negative edges with label 0. And then we compute the binary cross entropy to maximize the likelihood of positive examples while minimizing the likelihood of negative examples. After we compute the loss, we do the backpropagation. And essentially so this is the entire training loop. And for evaluation, it's essentially doing offline inference for measuring the test accuracy. So this notebook contains the essentially everything you need to know for training a graph neural network for link prediction. So this method should scale to a graph of any size as long as it can fit onto a single machine. And the next tutorial would be next tutorial session. The next notebook will be about scaling the training procedure to multiple GPUs on a single machine. So before I move on to the next notebook, any questions so far?
Hi, I have a question.
Yeah, go ahead.
So here, is it that you define the two models? One is the GNN model, one is a score predictor. Is it like two separate different models?
Yeah, you can replace you can essentially replace the GNN model with other GNN models such as like GCN or other graph attention network. And also you can replace the score predictor by using multi-layer perceptron or other kind of predictor. They're like replaceable components.
Okay, so it seems like you first use the GNN to learn a node embedding, and then you use a separate model to do classification.
Exactly.
I see. Got it. Why? By the way, why do we need the second model? Can we just use the first model for the classification task?
So the task here is link prediction. So essentially, the first model is essentially only giving you the node representation, and you need another component that predicts the score on the edges given the node features, given the node representations.
Okay, thanks.
Cool. So the question is this code accessible after the SageMaker instances are terminated? So the code and notebooks are all available on the GitHub repository. Oh, okay. Yeah, someone answered it. Any other questions? All right, so let's, okay, another one. How different would this look for a bipartite graph? So, good question. So essentially a bipartite graph is a kind of heterogeneous graph. So for heterogeneous graphs, we provide examples such as GCM, graph convolutional matrix completion, or like relational graph convolutional networks. They essentially can all do link prediction on heterogeneous graphs. You're welcome to check that. But in general, there's not that much difference. Like the methodology here also applies to heterogeneous graphs. So, okay. So any other questions or follow-ups? Okay, so let's move on to the next notebook, which is scaling to a single machine, but with multiple GPUs. So here, we will see how DGL works with a PyTorch distributed data parallel module that allows you to utilize multiple GPUs. So here you'll also learn like how to use PyTorch DDP to do multi GPU training for node classification here, and also you will learn how to customize the neighborhood sampling strategy. Oops. So the first part is loading data sets created in the previous notebooks, which is exactly the same as before. And here is a tiny introduction on how to customize neighborhood sampling. So to customize the neighborhood sampling strategy, you simply only need to inherit from this dgl.dataloading.blocksampler class, and then you implement this function called sample frontier, which takes in 3 arguments. The first one is the block ID, which is essentially the ID of the position of the GNN layer. Like if the GNN layer is the first layer, then the block ID is 0. If the second GNN layer, the block ID is 1, etc. The second one is the original graph, and the third one is the which is called seed node. Is essentially the nodes which the current GNN layer is gonna compute the representations. So here is just a tiny implementation of the multi-layer neighbor sampler, which is essentially given the output nodes, we sample this number of neighbors for each node appearing in the seed nodes and returning it as a graph. So this is essentially how you customize neighborhood sampling strategy, and you can also replace it with any kind of algorithms. So the following is how to define a data loader for distributed data parallel. So in PyTorch DDP, so each worker is assigned an integer rank, and the rank would indicate which GPU it is going to use, and also which partition of the data set the worker process will handle. So the difference is that each worker process will only iterate over a partition of the data, a partition of the whole data set. So here we are essentially figuring out which partition of the entire node set we are going to iterate on. So here NID is the input argument NID is simply the entire node set. And here we are computing which partition of the node set where this process is going to iterate on. And the rest of the sampler and data loader statements are essentially the same as the one we've seen before. So the model definition is still exactly the same as one we have seen in previous notebooks. And here's how we are going to distribute the model to the GPUs. So essentially the way to distribute the model is essentially the same as the PyTorch DDP for any other models. We create the model. We first initialize the model and then copy to the GPU this process is working on, and then we wrap it with a distributed data parallel model provided by PyTorch. And you can see the usage of the distributed data parallel module in the PyTorch tutorial, PyTorch distributed data parallel tutorial. So this is the training, how the training loop for one process would look like. So here essentially we'll initialize the process group, of the Torch distributed training, and then we set the device for this process to work on this GPU ID. And then we load the data. We create a data loader for the training set, and then we create the data loader for validation set. And here we are only using one worker process, which is essentially one GPU for validation, although you can also do like multiple validation with multiple GPUs. So after we create the data loader, we initialize the model, we create the optimizer, and then here this barrier statement is simply synchronizing the worker processes so that they can start training at the same time. So the training loop that computes the training loss, backpropagation, and compute the training accuracy is exactly the same as we have seen in the first notebook. And after we finish the training loop, we synchronize it again, and then we start the process of validation, which is again the same as the one we have seen in the first notebook. The only difference is that instead of calling to CUDA, you will be copying the blocks, copying the graphs as well as the features and labels to the GPU the process is using, and that's the only difference. So after you define the training loop function, the last thing you will do is to simply start up four processes, which correspond to 4 GPUs I'm currently using. So your SageMaker instance only has 1 GPU, so this notebook will probably break on your SageMaker instances, and I'm just running this notebook on my instance, which has 4 GPUs. So essentially, it will start 4 processes, each working on 1 GPU, and then it starts training. So much for training a multi-layer GNN with multiple GPUs. So, and that will conclude the session for now. So any questions on the materials?
Yeah, I have a question. Is this the DGL.5 version?
Yes.
So I noticed there's some minor discrepancy between the versions. Like for example, in the previous notebook, maybe there's a data sampler. So in the documentation, it says data loading.neighborhood and then multi-layer sampling, but in your code, it's written a little bit different. So I was wondering,
looking at the doc server, right?
What was that?
Are you looking at the documentation?
Yeah, I was looking at the documentation. I was running your notebook on my own machine.
Oh, so the node data loader. So in the documentation, we will see the neighbor.data loader, which is essentially the same thing as just using data loader. The neighbor.data loader is just a full namespace.
Right, right, yeah. So I think there seems to be a little bit of difference between from version to version. So if I do a full upgrade to 0.5, so is it likely going to break some of my old code?
So I think no data loader is only available in 0.5. It's not available in 0.4.3, for instance. So like it's only introduced in 0.5. So so if your old code doesn't use no data loader, then I think it's okay.
Oh, okay, but in general, it shouldn't be a big issue, right?
No.
If it's not the data loading, but something else.
No. Like your old code should still work.
Cool. Hi, I want to ask one more question here.
Sure.
Is when this DGL Library 5 will be officially released?
Yeah, it is.
It is already because I was checking the website. It's not updated on the website. That's why I joined late, so I didn't know the question.
Oh, okay.
Sorry.
Yeah. The website, the GitHub main repository is updated, but the DGL.ai homepage, I guess it's not.
Okay.
But the content and pip versions are content pip package is already available online.
So I want to ask one more question here. Sorry for that. So because
Sure.
maybe I missed some of the talk. So is distributed version also available now with version 5? Distributed.
Yes, that will be in the next session.
Oh, okay. Thank you very much.
No problem. So any question? So if not, then another one. Do you have paper for this tutorial contents? So I'm not sure what you meant by saying paper. So are you asking for a reference of the GraphSage model or simply published paper? Okay, so this GraphSage model is yeah, I can send the link in the chat room. So any other questions? Oh, okay.
I just sent the link. Yeah, I just sent the link.
I saw it.
Yeah.
Cool. Then I guess that's so much for me. And let's take a coffee break and then let's move on to the distributed training session.
Okay, so I see seems this session it takes less than 1.5 hours. Then maybe you can take a 20 minutes break and then we'll come back and then we can continue with the distributed training session. Hello, let's get started. So it has been a long day. So this will be the last session of this DGL tutorial. And in this session, we are going to cover how we are going to train a graph neural network in a distributed setting in DGL. So as at the beginning of the tutorial, Zizi briefly mentioned how distributed training works in DGL. So basically, the distributed training will be the extension of the mini batch training we have seen in the previous session. By the way, can everyone hear me? Okay. Okay. So this is basically the extension of mini batch training. Sorry. To the distributed setting. So as to just recall what happens for mini batch training, what we need to do is we need to sample subgraphs and then use those subgraphs as a mini batch and then perform the forward and backward computation and then update the use this mini batch to estimate the gradient of the model parameters and update the model parameters. So we will in the distributed training, we do the very similar thing. We divide the entire system into 4 components. So the first component is, of course, we need to have a training component that perform the forward and backward computation in a mini batch. And this mini batch is generated by a sampling component. So basically, the sampling component will just sample nodes and edges and construct a subgraph and then send the subgraph to the training component. When the training component gets the subgraph, it will try to read the required node or edge features from a feature storage component. And in the case that a model has learnable embeddings, and then it will also read those node embeddings and to once all the data is ready, it performs this training component. It will perform the forward and backward computation and estimate the model parameters, and then talk to the a parameter server to update the model parameters in the distributed environment. And if there is a node embedding in the model, then the trainer will also send the gradient of the node embeddings back to the feature storage component to update the node embeddings. So the reason we actually store, even though the node embedding is part of the model parameters, we actually store the node embeddings in this feature storage component because the node embeddings usually is very, very large. So we want to perform a very efficient communication, data access and communication to update the node embeddings. So that's why we store the node embeddings separate from the remaining model parameters. And DGL adopts this fully distributed design. That means in a cluster of machines, we will run all machines will run the training component, and they all run the sampling component and the storage component. And so all the machines runs equally. And then we also perform, DGL also perform locality-aware partitioning. What it means is that when we partition, basically we need to partition a graph for the distributed training, right? And we perform, when we partition a graph, when we assign nodes to partitions, we make sure that those densely connected nodes are assigned to the same partition. So then when we when we perform a mini batch training, we try to co-locate the partition data with the computation. So when we perform the computation in a mini batch, most of the data actually is read from the local machine instead of from read from across the network. So in this way, we can significantly reduce the amount of data communication And this will allow us to potentially to achieve a linear speedup. Another very important thing is when we design our system, the distributed system, we also try to minimize the code change as much as possible. We will see later how much code we need to modify to convert a mini batch training in a single machine to a distributed setting. Okay, so here is the overall architecture of the distributed training. So basically, as I mentioned before, all the machines will run the trainers, and all machines will also run servers. Those servers is basically trying to provide this sampling functionality and also the feature storage functionality. So all the machines will run servers, and potentially each machine can run multiple trainers and multiple servers. And the DGL partitioner graph, and then each machine, one machine is only responsible for one partition. And then those partition data will be stored in the server side. And then the trainers will access those partition data through 4 interfaces, 4 classes. One is dist graph. So it can use the dist graph to access the partition graph structure, the partition node data, and edge data. The trainer can also use this dist embedding and the dist tensor to access the distributed embeddings and distributed tensors. And trainer can use this sample neighbor function to sample a subgraph to generate a mini batch. And here is the overview of distributed training code. So as I mentioned previously, when we designed the API, we try to minimize the modification as much as possible. So overall, we mainly need to modify 3 places. The first is we need to add one function call that is the initialize. So basically, this initialize the DGL's distributed component. This has to be called at the very beginning. Before we call any distributed DGL distributed API. And in addition, we also require users call this initialize function before the PyTorch initialize function. And the second place is instead of using DGL graph as the previous session we discussed, here we need to use dist graph. So that is representing a distributed graph stored in the cluster. And when we create a dist graph, we only need to provide a graph name. And so basically, because the graph data is already loaded by servers, so we only need to connect to those servers and reference to the distributed graph. The third place is we need to call, so depend on, this is a node classification task or a link-based task, edge-based task. So if it is a node classification task, then user should call a node split to get training a subset for the local trainer process. If it's a link prediction, then we will have an edge split task. So edge split function to get a local training set. And then after we make this add this line, then the remaining code will be exactly the same. So if we want to use this node data loader to generate sampling mini batches, then we will just use it in the same way as before. And if the model we implement will be the same as before, and also the training loop. So the training loop will also be exactly the same as before. So basically, so in summary, really the number of lines that we need to modify to enable distributed training in DGL is really small. Okay, now let's dive into deeper and see how distributed training actually works. So to enable distributed training, the first step is data preprocessing. is because we need to partition a graph, right? We need to split the graph and load the graph into multiple machines. And DGL provide the tools to support graph partitioning. And right now, DGL supports 2 partitioning algorithms. One is METIS. So this is a, I don't know if, I guess for anyone who works on the graph domain, METIS is a very well-known partition algorithm. So basically, it generates a very good edge partitions with a very small number of edge cuts. And we also provide a random graph partitioning. This is basically it's a baseline. So in case the METIS partitioning doesn't work so well, people can just use the random partitioning. But usually, I mean, we will highly recommend people use the METIS partitioning first. Try the METIS partitioning first. So as I said, the METIS partitioning basically will assign. So what this the partition or METIS partition algorithm basically assigns nodes to partitions, and then to ensure that the partitions will have a very small number of edge cuts. And so this is basically here. This one basically illustrates the partitioning steps. So once we use the METIS, then we will assign nodes to partitions. And then we need to perform an actual split of the graph to generate a subgraph. So when we generate a subgraph, so each subgraph will be, the nodes will be, it will contain the nodes that belong to this partition, as well as a very small number of nodes that is incident to the edges that being cut by the partitioning algorithm. So for example, in this, the partition 0, it contains the blue nodes, all the blue nodes, as well as a very small number of yellow nodes, because those yellow nodes are connected with the edges cut by the METIS algorithm. And it will also contains a small number of red nodes for the same reason. So then we generate the partition exactly in the same way for all the other partitions. And then we assign a partition to a machine, and so each machine will have only need to handle 1 partition. And one very important thing for METIS partitioning, when we use METIS partitioning, is to generate a load balanced partitions. In our experience, if the graph is not, when we partition a graph and the graph is not balanced, then it will usually lead a pretty bad performance. When I say performance, I mean speed. So in our partitioning tool, we provide 2 partitioning criteria. So these two, the balancing criteria. So these 2 criteria are actually the built-in criteria. So it is user can just use. I mean, you can use it very easily. So the first criteria is if the graph has multiple node types, then our partitioning algorithm will try to balance the number of nodes of different types in each partition, so that each partition will roughly have the same number of nodes for each node type. And similarly, we also try to balance the edges. And the criteria is we will balance the in degrees of the nodes for each node type. And in the case, I mean, when we run a machine learning models in a graph, in a data, so we usually want to split the training, the data, the label data with like the training set, validation set, and test set. So, but when we perform mini batch training on a graph and on the training set or validation set or the test set, we need to also, so when we partition the graph, we also need to balance the training set and validation and test set on each partitions as well. So one way we deal with that is we treat the nodes, if this is node classification, we treat the nodes in the training, validation, and test set as different node type. And then we use the balancing criteria built in our partitioning tool to balance these sets. So so far, we found this strategy works pretty well. Another important thing we do in the pre-processing is to relabel node IDs. So the reason we need, we assign reliable node IDs or edge IDs to ensure that all the nodes and edge IDs in a partition will fall into a contiguous range. So the reason we want to do that is because if we don't reliable node IDs, what we need to do is we need to maintain a huge array to map a node ID to a partition ID, as well as an edge ID to a partition ID. Because in the distributed setting, we need to find out where can we find a node, right, in the cluster. So if we once we do the relabeling, then we only need to maintain a very small amount of memory to compute to look up a node in a cluster. So this is a good way to design a scalable system. So after we relabel node IDs and the edge IDs, we will also reshuffle the node features and edge features accordingly. So in the end, when users develop a distributed training code, users usually don't need to worry about this ID relabeling, all this kind of stuff. The only time a user need to think about this ID relabeling is when you, after you train the model and you want to perform some inference on your downstream task. At that point, you need to figure out, okay, where is the right node you want to get the node embeddings that is computed by the graph neural network. So other than that, I think usually users don't need to worry about the ID relabeling. Okay, so DGL, as I said, DGL provide a built-in tool for graph partitioning. And this tool is basically, we've just provided an API. And then users need to use this tool, to use this API, users need to load a graph into DGL in any way you like. And then you pass this graph to this API, and then it will partition the graph and then save the partitioned data into disk. And here is the summary of the partitioned result. Basically, it contains, first it has a JSON file that contains all the information, contains all the metadata information about this partition. And then we have, if we do not have this ID relabeling, then we need to save this node or edge mapping as well in a file. And those mappings are going to be very large if your graph is very large. So we highly recommend people to relabel node IDs. Relabel all IDs, both node IDs and edge IDs. And then this partition result will also have multiple folders, and each folder corresponds to one partition. And then inside of this folder, it contains the graph structure of a partition, and then it contains the node features and edge features. So all the node features will be stored in a file, and all the edge features will be stored in a file. Okay, so after we partition a graph, now we need to develop our, let's see what is the distributed APIs we can use for us to develop the training script. So the first thing is, of course, the distributed graph. It is the most important concept or API that we need to use. And so this graph basically is a Python class that is designed for the trainer process, the training script, to access the partitioned graph structure and the node and edge features in the cluster of the machines. So this is basically illustrate this idea. We have the partitioned graphs, and then we have this graph as an interface to communicate with all the servers to get all the data we need for a mini batch. One important thing I want to mention here is actually this graph has a two execution mode. And by default, of course, it contains this distributed mode. So what it means is in this mode, then it really means that we are running the training script in a cluster of the machines, and then the this graph, you interact with all the servers in the cluster to access data and send data back or something like that. But usually it is this mode it's very difficult if you are working on if you are developing a model. It is going to be very difficult for you to debug in this mode, right? So running running a job with on multiple machines is always it's very difficult. So we add a standalone mode in this graph. So this mode basically will allow a user to run the same training script in a single process. And then in this way, then we can really debug in the model, the code in any way you like. So that's okay. So that's why. So this standalone mode is mainly used for model development and testing. And the switching between the distributed mode and the standalone mode, it doesn't require any code or code modification. Here shows you, okay, now let's see how we can create a histograph. So in the standalone mode, usually, in the distributed mode, the graph data is actually loaded by the DGL server. So what this graph needs to do is to just connect to those DGL servers to access the data. So that's when we, then when we create this graph, we just need to specify the graph name. So it will connect to talk to the servers and get the right graph. In the standalone mode, it needs to so this graph it runs on a single process, right? There's no server to load data for you. So this graph needs to load the data itself. Because of that, users when use this graph, create a histograph, it also needs to provide this part config argument to specify where this data is stored. Okay, so previously I said that it doesn't require any code modification. So if you specify this configuration file in the distributed mode, it is fine. It doesn't. This graph will just ignore it. Ignore this argument. And to access the data in this graph, basically the API to access data in this graph is the same as the DGL graph. The only difference is the API currently provided in this graph is a very small subset of DGL graph. So, for example, if you want to access some graph structure information such as the number of nodes, you can just call number of nodes. This is the API actually provided by DGL graph as well, something like that. And if you want to access the node data and edge data, you can just use N data and E data. So I hope I hope you have so you have seen this this interface when Minjie was talking about how to access data in DGL graph, right? So the main difference is when we use N data, what it returns is actually instead of it normally in DGL graph it will return a PyTorch tensor, but in this graph, when you call N data, it will return a distributed dist tensor. So that is the only difference. But then when you want to access some node specific data, then you can just provide the node IDs and then it will return the node data or those node IDs in a PyTorch tensor or in MXNet tensor. Okay, so DGL also provides this distributed tensor interface. So it provides this tensor that will allow users to access a distributed tensor that is sharded in a cluster of machines, as we have seen here. And then this tensor is just the interface to access the distributed tensor. And the interface to access and the data can be accessed by providing global row IDs. So here is the basic operation we can do with this tensor. So users can create this tensor just like we do like what we create PyTorch tensor, for example. Maybe the only difference is that in this tensor, it supports additional argument called tensor name. So this, you can provide a tensor name. So the reason we want users to provide a tensor name is in this way we can really identify a distributed tensor in the system. So suppose if you provide a tensor name when you create this tensor, if this distributed tensor has been generated, then you can the new tensor object will just reference to the previously created distributed tensor. Another very important thing I want to mention is this tensor creation is a synchronized operation. What that means is when a trainer process calls this tensor constructor, it can only proceed when after all the other trainer processes calls this tensor constructor as well. So that means that this tensor creation will invoke a barrier to synchronize all the trainer process in the cluster. So this is very important. So yeah, when you use it, you need to be careful about this synchronization. And then the reading this tensor or reading data from this tensor or write data to this tensor is almost the same as we use the PyTorch tensor. We also provide a distributed embedding. We found this is very useful for many models. And so this distributed embedding is very similar to the PyTorch and embedding layer, and the interface is very similar. But the difference is we want to implement this distributed embedding in a more efficient way. As far as I know, the PyTorch embedding is not really well optimized for this use case. So this embedding is mainly used for some models that require learnable embeddings. For example, in the case of deep work, we want to put the node embeddings on each node, and then we want to perform, we want to update those node embeddings with the backward function. And in DGL, this distributed embedding is implemented on top of this tensor. So a lot of behaviors or the design actually is very similar to this tensor. So we can see that it is also sharded across all the machines in the cluster, and then we can read the embeddings. And the one big difference is we can only update those distributed embedding with DGL's sparse optimizer. So here I will show you the example how we can do that. So again, to create the behavior of creating this embedding is very similar to this tensor. So it is so creating this embedding is also a synchronized operation for exactly the same reason. And the reading this embedding is it's just like the interface is the same as the PyTorch one. So we provide the embedding ID and then embedding index, and it will return all the embeddings you like. And to update the embedding, so we user need to create an optimizer. So currently, DGL provides only one optimizer. It's called sparse AdaGrad. So in the future, we are going to add more optimizers. So for example, the sparse Adam or something like that. So the reason we call it a sparse is when we perform the forward computation, we will fetch some embeddings for a mini batch, right? And then in the backward computation, we only compute the embeddings that are involved in. We will compute the gradient of the embeddings that are involved in this mini batch. And then when we update those update the embeddings, we only update the embeddings that are involved in the mini batch. So so that means it will only touch a very small number of embeddings in a mini batch. So that's why we call those optimizer as a sparse optimizer, because it performs sparse update on the embeddings. And And this embedding, this sparse optimizer, sparse AdaGrad also has the similar interface as the PyTorch optimizer. So when you create one, you need to pass all the embeddings you want to update. And then using the embedding is in the same way as the PyTorch version. And then you, in the end, we need to call the optimizer step function to update those embeddings. Okay, so and then we DGL also provide so in the distributed setting, we also provide the distributed sampling. So for distributed sampling, we provide 2 levels of interface. The first level is the lower level interface. We just require, we allow users to customize how neighbors are sampled in each layer. In the single machine version, we provide a sample neighbors API, and similarly, we provide a distributor version for this function as well. And when we use, if we use the low-level API, then the most of the code, the sampling code, will be the same as before. The only difference is we need to switch the original sample, the single machine version of sample neighbors with this distributed version, and that's all. And if users want to, for distributed training, we also provide a high-level sampling API. So this is basically what we have seen in the previous session. So for example, the node data loader. So if users use this sampling API, then nothing needs to be changed. So this code will be can be used for both the DGL graph and the dist graph. And another last thing I want to mention for distributed training script is we need to split the training set, the validation set, and test set. So in the distributed setting, the recommended way for us to store a training set or validation set, test set is to use a global mask tensor. So this is just one 1D array that for node if this is node classification, this tensor will have the same number of elements. The number of elements in this tensor will be the same as the number of nodes in the graph. And for edges, then the length of this tensor will be the same as the number of edges in the graph. And each element will be just 0 or 1, and that represents, if it is 1, then it means this node or edge exists in the set. Otherwise, it's not. So we want users to use this way to store the training set and in the distributed setting. And then when we want to calculate what are the training node, the nodes that is the local process is responsible for, then we can just call this node split or edge split function in this masked tensor. And then it will return a set of nodes for the local process. Okay, so after we see all the APIs for distributed training script, then let's see how we can invoke the distributed training job. So in DGL, we provide two scripts to help users to invoke a distributed training job in a cluster of machines. And the first script is a data copy script that will copy all the partitioned. So suppose you partition your graph in your machine, and then you want to copy this partitioned data in a cluster of machines for distributed training, and you can invoke the copy file script that will copy the partition data as well as the configuration files as well as the training script and everything to the machines where a distributed training will happen. And the only requirement of using this script is user need to set up the cluster so that we can use SSH as the passwordless access to get to all the machines in the cluster. And then the script will copy the partition to the right machine where the training job will use the partition. And then it will update all the configuration files automatically. So then later on, user do not need to modify anything to launch the training task. And then the second script is, of course, the launch script that will help user to run the distributed training and inference in the cluster of the machines. And similarly, it will require the user to set up the cluster so that each machine can access to other machines with SSH passwordless access. And then we launch this the script. User need to specify the number of trainers in each machine, the number of samplers, the number of samplers, because we do multi-processing sampling. User need to specify the number of sampling processes per trainer, and then user needs to specify the number of servers per machine. And then we need to tell user where to tell the training script, launch script, where to load the data and what is the IP configuration of the cluster, and then provide the full the configuration of the training script. And then the script will launch all the servers and the trainers on the cluster and to run the task. Okay, so in the remaining session, I'm going to show you use a set of notebook to show you how we are going to actually perform the graph partition and what kind of basic operations we can use on the distributed components, such as this the graph, this the tensor, and this the embedding, and then how we can write a distributed graph sage model for node classification. And if we have time, maybe if we have time, and then we will also see how we can use this distributed embedding with graph sage for a node classification task. But if we don't have time for that, then a user can go back and to just play the notebook. So the notebook is all available in the GitHub. And last, I think I will try to show you how we can convert this notebook into a training script and then run the distributed training job in a cluster without modifying any code. Before we go to the notebook, one thing I want to mention is the DGL Palo Alto team are hiring. So if anyone are interested in working with us, please contact me. So you can you can send me email in this using my Amazon email. So dzzhen@amazon.com. Okay, then let's go to the notebook to see how how the code actually works. So before we go to the code, does anyone have any questions about the concept of distributed training?
Hi.
Yep.
Yeah. In the code that you showed, you are using the backend of GLO. Why not NCCL?
NCCL. Oh, so actually for distributed training, I only tested with. I didn't test it with NCCL because I thought NCCL right now may not support something. I think it does. So right now, I only tested the code with. Let me see which one I'm using.
Glue.
Glue, yes.
Yeah.
So I mean, you are welcome to test it with NCCL.
Oh, okay.
I haven't.
No,
I didn't test it.
I thought that there is some special reason not to use NCCL. That's why. Okay. One more question I have on. So initially, when you partition the graph, how do you say when you partition the graph, right? So how is it ensured that if we are using a two-layer graph sage, that some of the the second layer nodes will fall into the other partition? Is that true, or do you ensure that all the for the main node for which we are computing the embeddings, the neighbors or the two hop neighbors all remain within the same partition?
A very good question. So we right now the medius partitioning algorithm we are using right now doesn't really ensure the second doesn't ensure the second layer. So it's only its optimization objective is to reduce the edge cut. So right, that means it only optimizes for the first layer. So our experience is when we even though we only optimize for the first layer, it still generates a very good edge cut. And so we can save a significant amount of data and data copy. So if it is just 1-2 layers and you do not have partition a very large number, I mean, you do not split into many large number of partitions, in general, it works fine.
Okay.
But if we use like 3 layers, I didn't test it yet.
Sorry, I have one more question on this. Actually, so when you have a distributed training, so after the epoch, and when the gradients are calculated, are gradients calculated individually on each machine?
Are you talking about the so which model parameters? Are you talking about embeddings, or you're talking about
the gradient?
So yes, so the gradient is always calculated in the local machine. So remember, so when we generate a mini batch, this mini batch, all the computation in this mini batch runs in a single machine. So this so it will generate computed by the local machine, and then this gradient will be sent to, like, for example, the parameter server, or sent to the, if it is an embedding, then it will send to the storage, the feature storage component, and or I mean you can use a hollow word to. So if it is a dense parameters, you can use whatever the way you want to aggregate the gradient or the model parameters.
Okay, sorry, I have one more question. Sorry for that.
That's fine.
You mentioned that there is a parameter server, right? So does each node have one parameter server, or there's only one parameter server that is shared across all the distributed machines? I see.
Yeah. So first, I have to clarify that figure. Those parameter server really means is any mechanism provided by the deep learning framework to support the model, the aggregation of the model, the gradient of the model parameters. So it means it will, if you are using MXNet or TensorFlow, then it will be the parameter server. If you are using PyTorch, it can be PyTorch distributed component, or you might use a hollow word, then it is hollow word to aggregate the gradient. Right, so it is whatever the way you like to use. It is usually out of the control of DGL, and it goes back to your question. I would say, as far as I know about the MXNet KV store, it will partition the model parameters based on the name.
Okay, I understand that. Thank you very much.
No problem. So, any other questions?
Hi, I have a question. So you mentioned you have to relabel all the node IDs or edge IDs. Could you elaborate a little bit more on that? How does that solve the problem where?
Okay. Yeah, sure. So I need to explain it in a more clear way. So sorry about that. So basically, if you do not relabel node IDs, right, what will happen is we need to maintain a huge array to map a node ID to a partition ID. So the reason we needed to maintain this huge mapping is because when we, in the distributed setting, we split our data in node data and edge data in a cluster of machines, right? So when we want to read a node data, we need to find out which machine actually store this node data. So that's why we have to maintain this kind of mapping. And without the reshuffling, relabeling, then this mapping, this array will be is going to be huge. Because think about if your graph has like 1 million nodes, sorry, 1 billion nodes, or like 10 billion edges. So then this mapping array will be have 1 billion elements or 10 billion elements. And this, and what's even worse is this array tensor need to be stored on all machines. So this mapping array will be replicated on all machines. There's no way, there's no other way to get rid of it. So, but if we relabel the node IDs and edge IDs, then we do no longer need to maintain this huge mapping array. Or we just need to we need to know from where to where it stores this node stores in partition 0, and from where to where it stores the partition, it stores in partition 1, and etc. Then the size of the array, the information we need to maintain for the mapping is basically the number of partitions in the cluster. So it's very small, like 4 or 8, something like that. So that's why after we tried, we decided to switch to this the ID remapping idea to make the system more scalable. So do I address your question?
Still, I'm not quite, exactly understand how does relabeling solve the problem. Let's say after you relabel all the nodes within each cluster, right? Then like within each partition, you will have node ID, starting from 0 to n, right? Mm-hmm. And they are separate. Now, say you want to, find out which partition does node, let's say in the global mapping, original mapping, right? Node ID 100, like how do you find out node ID 100 lives in the current partitions? Like which partition doesn't contain the original node ID 100?
Okay, so you can think of this way. So suppose we remap the node IDs, right? And then each partition will contain all the node IDs in one partition is contiguous. So that means that for the partition 0, then you will have nodes from 0 to 100. And in the second partition, you will have the node IDs from 101 to 200. So and so on, right? So suppose you have 4 partitions. Then the last partition will have the nodes from 301 to 400. So suppose your graph has 400 nodes. And now if you have an ID labeling like that, then if you want to know which partition does node 10 belong to, right? Then you can just do a lookup. So you can calculate which partition has this node 0, node 10. You see what I mean? So basically, you can compute the node IDs. The partition IDs.
So does it mean you still need to somehow store the mapping between the original node ID and partition?
Oh yeah. You are right. Sorry. In the notebook, actually, I'm going to show you the mapping. This mapping is necessary, but this mapping this mapping will be stored as node data, but this mapping is partitioned, so it's not replicated on all machines. And this mapping is rarely used during the training. So the mapping may be required when user want to perform some kind of inference task at the very end. But it's not really used even in the evaluation.
Okay. So the benefits of relabeling mainly provides you that you don't have to remember a huge mapping across all the machines during training process.
Mm-hmm.
But you still need a mapping storing the original ID and the partitions. Okay,
Yeah.
okay.
Yeah.
I see. Okay, it sounds like essentially you're partitioning your node ID, doing some range partition, and then you can probably do some binary search to quickly identify the partitions for each node after the relabeling.
Exactly.
Got it. Okay, cool. Thanks.
Mm-hmm. No problem. So I think I'll quickly. So I see some more questions in the chat. So I'll just quickly go through those questions. So the first question is, does DGL support a random walk-based sampling? For example, for PinSage, and currently in the single machine, yes, we do support a random walk. And in the distributed setting, no, we currently don't support the random walk. We are working with that. For the second question, how do you define and configure a cluster as EMR? Also, does the library support the deployment on cluster management like Kubernetes? So the answer is no. So right now, distributed training is still in kind of preliminary stage, and we are just released the distributed training in kind of like experimental feature so far. We will definitely try to include all those production configuration environment into integrate the distributed training with all those the common deployment solutions in the near future. After we finish do some more optimizations in the distributed training. So another question about the slides. Yes, the slides. The slides will be available, and I forget to upload the slides. Yeah, all the information we will try to upload it after the tutorial.
Hi, can I ask 2 more questions, or should I ask
sure.
after the talk?
Is that a quick question?
It should be quick, I guess. You mentioned when you create the dist tensor and the dist embedding, it has to be a synchronized operation. Could you explain a little bit more on that? Why does it has to be synchronized?
I see. To be honest, whether or not it is mandatory, it's I guess depend on the design choices we made. So at some stage we had a design so that we need all the clients. When the clients connect with the servers, somehow we made a design that require all the clients to synchronize before to create a new tensors in the server. Whether or not it is, we need to rethink about it. Whether or not it is something has to be done in a synchronized way. I cannot tell you for sure. Maybe we can in the future, if we find a solution, we can remove this synchronization barrier. That's possible. I cannot tell you for sure that we will do that. But right now, I just want to tell you that based on our current design, we require users to do that.
Okay, but what's the reason behind the choice now?
So basically, I mean, think about if we do not have this synchronization, right? When we create, so one client create try to create this tensor, and another and then it will talk to the server and then create this tensor in one of the server, and then another client or another trainer try to create this tensor, and it also talk to some of the servers to create a tensor, and so on. And then so eventually when you create this tensor, you only on one server, then you just create a part or a partition of the distant tensor, right? But eventually, you need, when you access the distant tensor, you can access any portion of the distant tensor. So without the synchronization, you may one trainer may end up accessing something that doesn't even exist yet. So again, this is a design choice we made. Depend on what is the semantic we want to provide, and what is and another thing is our main design choice is we assume all the trainer process will run the same code. This is usually true for all the distributed training in any of the deep learning framework. Think about what we do with train ResNet in a distributed setting, right? So otherwise, it will just really make our design much more complex. So we want to provide a simpler design first and see how far it can go, and then we will try to improve our design and make it more flexible and so on. But one thing we want to ensure is that when we come up with this design and come up with this API, we may change the design in the future and change the implementation in the future, but we will try our best to maintain the current API. So we will only relax the API to remove some kind of constraint, but we will not change the API.
Got it, got it. Thank you, thanks.
Okay, so let's move on to the code. So the first notebook is to show you how we can call this DGL's partition API to actually partition a graph. In the previous section, actually, Chan used the OGB product graph. So this open graph benchmark data set for his demo. And similarly, I'm using the same the graph for this demo as well. Because this data set is a little bit large, so I did a little hack to make sure that I will reuse what the graph he downloaded. So the hack basically is here. So you can, I'm not going to explain what the hack is. I mean, you can just assume this hack exists, and you can just run this run those shells command line to reuse the It seems like the file already exists. So actually, I already run this notebook. So I already copied the data from what he downloaded. So actually, I don't even need to run this. I don't need to run this those script. But if you didn't do that, you should run this this block. And then after you, so basically this will just copy the data from the previous session, and then I will load the data into DGL. And then I'm using the PyTorch, the OGB's data loader. So it will ask you whether or not you want to update the data set. So here you should answer no. And then it will load the data copied from the previous session, and you can see some information, basic information. So this graph has about 2.5 million nodes and 123 million edges. So this is a decent size for us to run some experiments. It's not very large, but it's good size. And you can see this graph has like features, has the node features and the labels. And my data loader, the data loader I wrote will generate the train mask and validation mask and test mask as node data. And this graph doesn't have any edge features. And so so after we load the data, we need to partition. We need to basically prepare the graph for both the standalone execution and the real distributed training. So I will run both blocks. This may take a while. So let me briefly mention why we want to do this. So as I mentioned, that DGL distributed training actually has two modes. There's a standalone mode and there's a real distributed training mode. And in the standalone mode, it will take a graph with one partition, right? So because it runs in a single process. So that's why I prepared this. I run this partition graph to prepare a graph with one partition. And then this one will partition a graph into 4 partitions. And this is prepare the data for the distributed, for a cluster with 4 machines. And as I mentioned previously, that the partitioning algorithm actually has some kind of load balancing criteria. And there are 2. So there is one criteria is to balance the number of nodes for different node type. The other is to balance the number of edges. So this argument basically allows user to specify what are the node types in this graph. And then this argument to specify we want to balance the edges for each node type. So then for this, for here, when I specify the node types, I only treat nodes that are in the training set as one type, and nodes outside of the training set as another node type. So basically, there are only 2 node types. So in this way, it will when it partitions the graph, it will balance the nodes in the training set. Okay, so it will run. It takes a while. I will just go to the next slide. Next notebook. So because it already finished the first, it already finished generates the graph with one partition. So it's good for us to run the remaining tutorials in the standalone mode. So one more thing I want to mention is when by default, actually, when you run your code in, for example, the Jupyter Notebook, or you run your distributed code with Python directly, it is always a standalone mode. It only has one process running. The only time it will, when you run your training script with our launch script, then it will be converted. The training script will be converted into a distributed mode automatically. So users really don't need to worry about how to convert, how to turn a training script into a distributed mode or the standalone mode. Okay, so let's see what kind of basic operations we have. Let me go. I see there are some questions. So one question is, what exactly do I mean by balancing? Do you mean each partition will have similar number of trees? So yeah, so when I say balancing, I mean each partition will have roughly the same number of training nodes. Basically, each partition will have roughly the same number of label nodes, so that when we iterate over the training set, all the partitions will have all the trainer process have roughly the same amount of workloads, the computation. This is what I mean. Okay, so before we perform any invoke any distributed API, the first thing is we need to call this initialize function to initialize the DGL distributed module, and then we can create a dist graph from this from the graph with one partition. And then we can see the basic information about this dist graph. So because it has only one partition, so by the way, so yeah, when actually regardless it is partitioned or not, when we run numbers of nodes on a distant graph, it will always return the total number of nodes in this graph. So we can see that the total number of nodes, so then this total number of nodes should be exactly the same as we see here. And the number of edges will be exactly the same as the original graph. And let's see what kind of node data we have. So as we have seen before, that we have the features and labels, and we have the training mask, validation mask, and test mask. And in addition, when we partition the graph, it actually generates the original ID. So basically, so remember that we need to maintain a mapping between the original node ID and the relabeled node ID, right? So this stores. So when we partition a graph, by default, it will relabel the node IDs and edge IDs, and then store the original node IDs and edge IDs as the node data and edge data. So that's why we have additional node data in this list graph. And if you want to see what is the node data, what is this training mask, then we will see, okay, this is a list tensor. It doesn't really print out all the content of the list tensor. But if then you can access the training mask for the first 10 nodes, then it will return a PyTorch tensor, because we use PyTorch backend right now. So it will return a PyTorch tensor that show you whether or not those nodes are in the training set. So they are 1, so they are in the training set. And what is the original node ID? So it will, again, we need to specify the nodes where we want to get their original node ID. So we want to get the first 10, then it will return the original node ID or the first 10 nodes. And right now, because this is a standalone mode, and we only this graph has only one partition, so we actually don't really reshuffle the node IDs. So that's why you see, okay, the node IDs are actually the same as the original node IDs are the same as the current node ID, but in the distributed training, real distributed setting, they will be different. Okay, so if we look at what is in the edge data, then it has this original ID as well. In the original graph, it doesn't have any edge data. For distributed, so then let's take a look at what is the distributed tensor look like. So to construct this tensor, the interface for the constructor is very similar to the PyTorch tensor. As I said, so it may users can provide the tensor name, but it is optional. You can always ignore that. Then in that case, if you don't provide a tensor name, then this tensor becomes anonymous. What that means is in the future, we cannot create another distant tensor to reference the same distributed tensor. And so by default, when we create a distant tensor, its value is initialized to 0. So if you access the first 10 rows, then it will return 0. Oh, another very important thing I forgot to mention is right now, the distant tensor is really created, is designed for store data on nodes and store data on edges. So that's why the first dimension of this tensor must be the same as the either be the same as the number of nodes or the number of edges. But again, this is a design choice we are having right now, and in the future we are going to relax this design choice. So this tensor will become the real distant tensor, and if so users can, when user create the distant tensor, they can also specify how to initialize the values in the distant tensor. In this case, user should specify this the pass init function that the signature of the init function will be the shape of the tensor and the data type of the tensor. And then it should generate the values and create a new tensor and then return this new tensor. And then those values will be used to initialize this tensor. Now, if we look at the first 10 lines, then it will contain some random value, floating point values. And we can assign this tensor as a node data. So similarly, the interface for this embedding is also quite similar to the PyTorch and embedding layer. So user need to specify the number of embeddings and what is the dimensions embedding size. And one difference is when we user create this embedding, user need to specify how to initialize the value in the embeddings. So this part is kind of different from PyTorch. PyTorch usually will ask user to initialize the embedding values afterwards, and then we can create a sparse optimizer to update the embeddings. And so here is just a very simple example. So for suppose we get, so here I want to print out the first 4 embeddings, and then perform update, a step function to update those embeddings. And now let's see, those embedding values are actually different from the embedding values we get from here. So because this step function has updated those embeddings. Another very important thing I want to mention is if a user want to get some embeddings from the dist embedding, and does not want to perform any backward computation, it's basically it's not used in a in the training loop. For example, if you just want to get the embedding and do an inference on using those embeddings, users have to call this in with this no grad scope. So to ensure that internally it will not record this data access. Otherwise, you might see some errors when you next time when you run the evoke the step function. Okay, so is there any question about this? Is that all clear? I see someone is asking the link for the tutorial. So I will send the tutorial again to the channel. So anyone who is late for the tutorial, you can go to our GitHub to check out all the notebooks and also some of the slides. We will upload all the slides afterwards. Okay, so if no more questions, then let's go to the next tutorial. So this tutorial, I'm going to show you how we can write a distributed training script for GraphSage for this node classification task. So before I actually write any code for the GraphSage, I first define those hyperparameters first, because in the next step, I am going to show you how to convert this this notebook into a training script and then run with DGL the launch script. So we will. We may need to change some of the hyperparameters with the script, with the argument. And unfortunately, I noticed this arg path doesn't really work with doesn't work in the Jupyter Notebook environment. So when I demo this, I'm not going to execute this block. But this when after this notebook is converted into the training script, it will provide all the arguments to change those hyperparameters. Okay, so again, when we perform write the distributed training code, the first thing is we need to call the initialize function. And one more important thing is this initialize function has to be called before the PyTorch initialize function. Here we use a standalone argument to ensure that when this the PyTorch, because the PyTorch initialize function actually that cannot run in the notebook. So that's why when we run in the notebook, we actually disable the PyTorch initialize function. And here, so far, I only tested with the glue. I guess it will also work with other backends. We just need to test it. But this is really the PyTorch component. And then we will run this DGL distributed. Sorry, I will create a dist graph. And again, this we are print out all the basic information about this graph. And the next step is I'm going to split the training set, the validation set, and test set with this node split. And it will return a subset of the nodes for each of the set. But of course, this is a standalone mode, so actually this trainer process actually get all the training nodes, the validation nodes, and test nodes. Another thing is this is a node classification task, right? So we need to know the number of labels in the data set. So here I write the code to calculate the number of unique labels in the data set. So this will require us to read all the labels, the labels of all the nodes in the graph. Of course, this is not really a very scalable way. This is just for demonstration. Ideally, I mean, in practice, actually, we know the number of labels, number of unique labels in the data set. So users can just provide those number of labels as an argument for the training script if we want to run on a very large data set. So this is just for a demo. I would just want to clarify that. So then, the model definition will be exactly the same as before. I think Mingjie talked about this and Chen talked about this. So I can briefly reiterate over how this graph stage model is defined for distributed training. So basically, we will define a multi-layer graph stage, and then we define a PyTorch and module list, and then then we add multiple layers to this module list. And DGL provide n modules to define some existing graph neural network layers. So for graph stage, it is called SageConv. So when we define a SageConv graph stage layer, we just need to specify what is the input dimension, what is the output dimension, and what is the aggregation function we want to use, and that's all. Then we will just add them to the layer. And then in the forward computation, we will get, I think Chan also mentioned this, when we generate a mini batch, and actually we will construct multiple subgraphs and depend on the number of layers. So for example, if we have, we are running a 2-layer GCN, or 2-layer graph stage, we will generate two subgraphs for two subgraphs for each layer. And the subgraph is called here is stored in these blocks. So we need to iterate over all the blocks and then invoke the layer, this graph stage layer on each of the subgraph to compute the embedding for each layer. And then eventually it will compute the node embedding for the last layer and then return the node embedding. So this is the definition of a graph stage. And then we need to define, create these models and create all the loss functions and create all the optimizers. Everything here is exactly the same as we do for mini batch training. And you have seen this in the multi-GPU training example. So we, in the case for PyTorch, when we do multi-GPU training, we needed to use this distributed data parallel. So again, this thing doesn't really work in the notebook. So we will disable it if it runs in the standalone mode. And here we will reuse the sampling APIs as we have seen in the previous session. So it will create this node data loader and then defines how we sample the neighbors. And then we create a node data loader for both the training and for validation. And all the code will be exactly the same as we have seen in the previous session. The configuration will be the same. And now let's put everything together and run a training loop. Again, actually the training loop is, you can see it's actually very, very similar, or I should say it is very, very similar. There is some modification. It's very similar to the mini batch training. So we first iterate over the epochs, and then we iterate over the mini batches. And I guess the one difference maybe is we need to, in distributed training, we need to explicitly to read the features for the input layer. So our data node data loader returns returns the subgraphs for a mini batch, as well as the input node for this mini batch and the target node, the seed node, where the labels, those labels with all, that is basically the nodes with all the labels. So it will return the three data structure, and then we can use those input nodes to read the input feature, and then we will read the labels of the seed nodes. And then we run the forward computation of the model, and then we compute the loss and see to compute the loss to compare what is the predicted label and the true label of the data, all the nodes in the mini batch. And then we perform the forward backward computation and this piece of code actually is not required in the newer PyTorch. I have this code because previously this code was tested on old PyTorch. I think in the PyTorch 1.5 and PyTorch 1.6, and this aggregation, the code to aggregate the gradients across multiple processes or multiple nodes are no longer needed. It's done automatically in the backward function. And then in the end, we need to call the step function. And this is basically our training loop. And at the end of every epoch, we need to we compute the validation accuracy to see when we can stop the training. So to compute the validation accuracy, our computation is almost the same as training. We have this validation data loader that will sample the mini batch, and then we perform we read the input data and input feature, and then read the labels, and then make a prediction. Perform the forward computation and make a prediction, and then we calculate the accuracy. So let me just run this piece of code. This will take a while. By the way, so in this notebook, this code actually runs in CPU. If you run this piece of code in your SageMaker environment, because it's kind of it can be slow because the instance we create for this SageMaker is the smallest GPU instance. So it has only 2 CPU cores. So it's pretty slow. So one potential exercise is you can look at the code and to see if you can change the code and to make it run for GPU training and see how it works. Okay, so I'm just running the notebook in my local instance. So this is still pretty fast. Okay, so and one more thing I want to talk about for this distributed node classification task is inference. So we have seen this validation, the code for the validation, right? This is useful if so let's say the number of nodes you want to perform inference is small, and you don't really want to get the maximum accuracy. So the reason I say that is so if we perform perform neighbor sampling for inference, what we notice is depending on the number of neighbors you want to sample. If you sample a small number of neighbors and then perform the inference and then calculate the accuracy, and the accuracy is usually is a little bit lower than the actual accuracy. So that's why sometimes you want to perform a full graph inference to compute the actual the model accuracy. And the other reason is you might want to avoid this kind of method to perform the inference is the number of nodes you want to perform inference is basically the majority of the nodes in the graph. In that case, this neighbor sampling approach can be still quite expensive. So here I want to demonstrate another approach to perform offline inference on the entire graph. So so basically the idea is this. In this mini batch training, so what we do is we sample the ego network, right? So like a 2-hop ego network or 3-hop ego network, depending on your graph neural network model. And in the full graph for inference, actually we recommend write the code in this way. So since we are going to compute the embedding of all nodes in the graph, we will run the computation layer by layer. Let's say we have a 2-layer GCN or 2-layer graph sage. We want to run the inference for all the nodes in this layer first before we move to the next layer to compute the node embedding of all the nodes in the graph. So, but even that, but when we perform a full graph inference like this, we still can perform the inference in a mini batch fashion. So basically, we can get all the nodes, a subset of the nodes in this layer, and then compute its node embedding. So in this case, we only need to sample 1 layer of the neighbors to compute this this batch of nodes. And then we we have the sliding window strategy to move on to the next batch, and so on. And once we finish all the embedding, finish computing the embeddings of the layer, all the nodes in the layer, then we move to the next layer, and then we do the same thing. We for example, we compute the embedding of the nodes of these nodes, and then we only need to sample its direct neighbor. Sorry, we only need to collect its direct neighbor, and so on. Okay, let's see how the code will look like. So because we are performing the computation we are computing all the nodes, the embedding of all the nodes in the graph. So when we split the nodes for each process, we actually need to use a mask tensor that all the elements in the mask tensor is 1, and then this will return the nodes for the local process. And then we can still use this node data loader to construct the mini batch. And in this case, we will only sample one. Actually, we do not sample. We get all the neighbors get all the direct neighbors. So this is how we can construct a data loader that collects all the neighbors in the one hop neighborhood. Because we only need to collect the one hop neighbors, we can really increase the batch size, and we can use a very large batch size. Usually, it's fine. And another thing is, depending on we are running in the standalone mode or not, we will need to get the layers in a different way. Remember, if it is in the real distributed mode, our model actually is constructed by PyTorch distributed data parallel function. So that will generate a new model that is actually different from the original model. And then to access this PyTorch distributed model, we need to use this module field to access the content in our actual original model. And then we will this piece of code basically run the algorithm I described here. So we iterate over the layers first, and then in each layer we iterate over the nodes. And in each node, in each mini batch, we have only need to sample one. We will only have one subgraph because it gets the direct neighbors. So it has one subgraph. It gets the input data and then perform the one layer graph stage computation that will generate the node embeddings we need for this layer. And after we iterate over all the nodes in this layer, now we can switch the output embedding of this layer as the input embedding for the next layer. So that's why we have this x equal to y here. And one important thing I need to mention is in the distributed setting, even though we try to assign the same number of nodes for each trainer process, different trainer process may still run at a different speed. So that's why we have to put a barrier here to ensure that all the trainer process runs exactly in the same speed. So all the trainer process will perform the computation in this layer before we move on to the next layer. Otherwise, we may run into we may access some invalid data. Okay, so after we perform this computation, we get all the node embeddings of the target nodes in the final layer, and then we can perform prediction on the test set. So now it calculates the accuracy, which is 0.48. It's pretty good, actually. And here, and that's all for this distributed node classification task. I think we are actually run out of time, so maybe we can stop here. And we have another tutorial that shows you how to perform graph stage with node embeddings. But I'm not going to cover that. But one thing I want to mention is most of the stuff, the code is exactly the same as you can see here. So it just added an embedding component, and it will show you how to use the sparse optimizer with the DGL, the distributed embedding. And you can also try to compare this with the PyTorch, the sparse embedding. And yeah, so maybe I can answer some questions before the end of the tutorial. I see someone raise hand. How does this work?
Hi. Yes, thanks for the presentation. It's a great tutorial, and thanks to all the presenters. I have a question about the partitions. So when you split the graph into partitions into different machines, you mentioned that the trainer and partition stay in the same machine to make the training faster, right? So you don't have to like get data across different machines. Is that true for the validation data and test data as well? Like, was the validation and test data also split it into different partitions?
Yes. Yes. So when we partition the data, we actually do not really the validation data and the training data, validation data, and test data is we will try to balance them. If you tell us where those training nodes are and validation nodes are, and etc. But each trainer will perform the computation for the validation and testing themselves, and then it will calculate some result. By the way, so instead of really show you the demo, I can show you what happens when we run a distributed training in a cluster of machines. I will show you what is the output look like. So you will see what I mean.
Cool. Okay.
So this is basically we run the distributed training. So we run this. We launch the training job with this launch script, and then we specify all the arguments. And you have seen those arguments, and then it will start to run run the training script in 4 machines. And then you see that, okay, the machine 0, machine 0, machine 1, machine 2, and machine 3 run different client computation. By the way, so the ID, this may not be matched, but that's fine. And so because we run 4, we have 4 machines, right? So each of the print, actually you will see you will see 4 times. So you will see that they say one report says using the backend PyTorch, and then you see 4 of them. And similarly for this and for all the others as well. So after the training, after it run 10 epochs, we perform this full graph computation, right? Oh, by the way, so for the validation, it's the same. So for the validation, each trainer process will compute their own validation accuracy. So then you will see 4 validation accuracy. That basically means each trainer will run a different set of validation nodes. And then because we use the matrix partitioning, and it's not exactly, we try to balance the graph as much as possible, but of course it's not perfectly balanced. So that's why when you see the validation accuracy, it's not exactly the same because they are different set of nodes. And if you want to compute the global validation accuracy, you can just add them and then compute the average. Similarly, when you perform the full graph inference, you will also compute the accuracy on the local partition. Then it will be each of them will be different, and then you can average them to compute the global the test accuracy, like something like that.
I see. And cool. So so what happens if, let's say, if one of the or some of the worker is down?
Okay, so our current design doesn't really take the fault tolerance into consideration. I guess the reason we do not make this assumption or take this into consideration is following the current distributed deep learning paradigm, most of the the deep learning framework do not really consider fault tolerance.
Okay. Yeah, actually, I have zero background in GN or graph neural network. Does it mean like because I saw like PyTorch geometric is similar, right? That do they provide distributed training? If they provide like they do not handle fault tolerance as well?
I don't think that they provide distributed training. So this is a very new, even for DGL. So we just start to release the distributed training in our 0.5 release, and we will continue improve this because we want to have first give customers some functionality, and then we will continue improve and just make it run faster. And if we really think the fault tolerance is a very important feature, then we will also support that.
I see. Yeah, when I first saw this, I was thinking about maybe you guys have something similar to like the HDFS, the file system for graphs. If you when you have like a similar file system for graphs, maybe then you can like use a similar idea to manage this like fault tolerance.
Yeah, I mean if we think about the distributed graph processing framework, I don't really remember now which distributed graph processing framework that supports the fault tolerance. Maybe GraphX does because it's built on top of Spark. But a big different thing for graph neural network is because we need to train a model. We need to update the model parameters, right? So when there is a fault, there is a machine failure in the cluster, we need to figure out what is the right way to update the model parameters for this current mini batch, and what kind of thing we need to do. And so our current, as far as I know, for example, TensorFlow, the way they deal with fault tolerance is to perform a snapshot. So in each multiple number of mini batch, it will just save the entire state, and then later on we can restart the cluster and reload all the state and then continue the training. So that is something we are considering as well. I mean, this kind of strategy to handle fault tolerance is a very typical strategy in the HPC world. So we will think about that and find out what is the most efficient way to do that.
Got it. I have one more question. So for graph model, I imagine like does the training data, validation data, test data, all live in the same graph? It's just different node IDs and edge IDs. Is that right?
So it depends on the setting. So our current setting is we assume all the data, the validation setting, the validation node, test nodes are all in the same graph. But this is more like we are perform the training, model training in the transductive setting. And in the inductive setting, actually, some people may want to perform the inference, compute the accuracy on some new nodes or new edges, right? So it may or may not be those nodes or edges may or may not be in the original training set.
Okay, does it mean like your current API or only handles the transductive case? Oh, your training, process.
I'm just thinking. I think our API is general. So the question is how you want to deal with new nodes and new edges, right? So it's if you want to add new nodes or new edges to a distributed graph, it is always difficult. I mean, the question is why do we need to support something like that? Because a mutable graph is usually very difficult to support. One suggestion is I think the model developer should try is to, when construct a node set, the training set, ensure that those nodes in the test set and nodes in the edge in the test set does not appear in the training set. Even though it is the same graph, you just need to make sure that those edges or nodes do not appear in the training set. Right? You can construct this graph in advance. That's fine.
I see. Okay, I guess. Okay, it sounds very difficult if you do inference. You have new nodes. You have to make predictions for the new nodes. And
yeah, I mean, in the distributed setting, the data should be prepared. So remember, as I mentioned in the slides, the first step is data preprocessing. You have to prepare your data for the distributed training.
Including the test set?
Including the tests. So, okay, I should say this way. For training, the data should be prepared. For the test, it's really up to you because it's irrelevant to distributed training, right? So once you have the model, you can do whatever you like. You can,
yeah.
Right?
Got it. Thanks.
Okay, so we already have 10 minutes, 16 minutes more than we planned. So do we have more questions? We can also, I mean, if you are interested, you can also let me go back to the original. So you can, if you are interested, you can go to our Slack channel and we can have more discussion offline, if that is, if you like. And also, I want to say it again that the DGL team is hiring. So if you are interested, also talk to me. And I think that's all. That's all for the tutorial. And thanks everyone for staying so long. And this is it's a long tutorial. Okay, so I guess this is the end of the tutorial. Thanks everyone.